Yeah, but even in normal time, it was not dependent on, you know, what particular time direction you were choosing.
Exactly. Yeah. So, you know, for relativistic quantum field theory, tau could be X, could be Y or Z, but more generally, that's the topological nature of this symmetry operator. So one way to invariantly characterize the existence of a global symmetry is to find such a topological operator in Euclidean spacetime that depends on the choice of the manifold only topological. In QED, there's an axial current. It's not conserved. It obeys the anomalous conservation equation. F is the field strength for the dynamical U1 gauge field. Okay, naively, let's still try to define a symmetry operator by integrate the Hodge dual of the current on any general 3 manifold in spacetime and exponentiate it. But since it's not conserved, this operator is also not conserved, or more generally, it's not going to be topological. So what can we do? Well, let's try something else. We can shift the axial current by a Chern-Simons term, where capital A is the dynamical U1 gauge field of your QED. Well, now this J hat is not gauge invariant because A transformed under gauge transformation. So J hat is a gauge non-invariant current. It's formally conserved, but I shouldn't read too much into it because it's not a gauge invariant operator anyways. Well, but let me proceed nonetheless. I'm still going to integrate this J hat on a general 3 manifold and write down a formal operator U hat that's formally conserved. Unfortunately, it's not gauge invariant on a general 3 manifold. So it seems that I'm stuck. I run into this dilemma. I can pick this naive operator U. It's gauge invariant but not conserved. I can improve my current, but it's not really improvement because it makes it not gauge non-invariant. But now it's not gauge invariant but conserved.
But it's not gauge invariant. The current is certain blue, but as for the charge, in principle, it's like a Whiting number, and it would be a gauge invariant by itself, global one.
On R3, yes.
Yeah.
But on a general 3 manifold, no. Mm-hmm. And here, throughout the talk, I'm going to characterize a global symmetry in terms of a topological operator on a general closed 3 manifold in Euclidean.
So you're saying that it would be not gauge invariant, generic.
That's right. Yeah, I think I said it here on a general 3. Okay, well, let's be less ambitious and assume that the axial rotation angle is a fraction, the 2 pi over n for some positive integer n. Now this U hat takes this form. All right, it's still not gauge invariant because this term is not a properly quantized Chern-Simons. A Chern-Simons term is properly quantized if it's an integer over 4 pi. This one is fractional. So we still haven't made it yet. But this term is extremely famous. In condensed matter physics, this is the term that's commonly used to describe the fractional quantum Hall state. It's not gauge invariant, but fortunately, there's a well-known fix to this issue. And the fix is that you consider an alternative and gauge invariant Lagrangian, this one, by introducing an additional dynamical gauge field little a. Yes.
To be clear, you are only considering manifolds without boundary, is that correct?
That's right. Closed 3 manifold without boundary. I could consider manifold with boundary, but then the question would be even more interesting, which we haven't done so yet.
Excuse me, could you please show the previous slide because I didn't get where n comes from.
Oh, great. No, n comes out of nowhere. I just choose my axial rotation angle to be 2 pi over n with n some positive integer.
But so far you are discussing QED, right?
Yes.
So n and QED is...
Consider all possible n's, 7, 9, 11.
So why should we consider this arbitrary parameter?
Yeah. Because for such a choice of alpha 2 pi over n, things will get better. I will be able to define a gauge invariant and conserve operator for you in just 2 slides. Okay. For more general alpha, I don't know how to do it. But for any rational alpha, I'm
it's large, then it's actually almost any angle. Oh, you cannot.
That's right. Rational numbers are dense in U1. Yeah.
So it should be.
It's almost good enough.
It's almost good enough. Exactly. Yeah. It's almost a continuous symmetry.
Yeah.
Yeah. So okay, but let me start with 2 pi over n. I will talk about a more general rational number in just a few slides, but this is the simplest case. So in condensed matter physics, famously, this gauge non-invariant action for the fractional quantum Hall can be alternatively described by this more precise gauge invariant action. It's gauge invariant because every term, every coefficient is properly quantized. But the price we pay is that we introduce additional dynamical U1 gauge field little a on the 3 manifold.
But your original A could be non-dynamical as well, right? It could be background field. Your original A could be just background, right?
No, capital A is the dynamical U1 gauge field of the QED.
Yeah.
It's the thing that gives you the photon.
Yeah, no, but if it's external photon, then not in the loop, then it's like a background field.
You can take the fine structure constant to be 0.
Yeah.
Then the talk doesn't make. Then we're just talking about free Dirac fermion.
No.
And there's a perfect story there. You have a U1 axial symmetry.
I mean, the gauge field, if it's not inside of the loop, then dynamical nature of this field is not.
Well, but that's not up to you, right? The gauge field will generally run in the loop. Yeah.
There's no.
Okay, so we just went from here to here. There's a quotation mark to remind us that the fractional Chern-Simons term is actually not gauge invariant. The more precise version is this one. Naively, the relation between the two is that you can integrate out the little a and solve little a in terms of capital A with a factor of 1/n. This is, however, illegal because both little a and capital A should be properly quantized, namely their periods should be 2 pi times an integer. And that's good. You don't expect it to be legal because you start with an illegal action, you end up with a legal action. So the move between them, the relation between them must be illegal. And motivated by this discussion, why don't we just, back to QED, why don't we just replace this gauge non-invariant term that give us all the trouble by the gauge invariant fractional quantum hologram. So now I have defined a new operator, which I denoted by D subscript 1/n. Now this new operator D is manifestly gauge invariant because all the terms here are properly quantized. You can put it on arbitrary 3 manifold in space-time. Note that little a only lives on the 3 manifold M. Excuse me. It's like an auxiliary field that you use to define this operator. It doesn't introduce any new degrees of freedom in the bulk QED.
Therefore, this definition of this operator is also integral over.
That's right. So I have to include a path integral over little a for each of this operator D. That's extremely important.
But there's a difference between excluding a, small a, and what they are writing, it corresponds to something like that small a is not unique in certain sense, right? Because
it's there for each operator. Every time you insert an operator, you introduce a new path integral. It's like an auxiliary.
You're just missing a path integral.
right.
Yes, I miss. Yeah, in fact, in our paper, we have a footnote saying that we omit that path integral. Okay. All right, and this is somewhat reminiscent to Zohar's work in 2018, where he also used the fractional quantum Hall state to describe the eta prime part. All right, so now let's take a closer look at this operator D. As I said, it's gauge invariant. I'm also going to claim it's conserved, namely topological. This is less obvious, but if you are willing to loosely equate this term with that term, then the conservation follows. But this is completely heuristic, and we will have a much more rigorous proof in a few slides. The price we pay, however, is that this is not an invertible symmetry. So what do I mean by that? For ordinary symmetry operator is unitary. That's what Wigner told us. So if you start with an operator, you take the dagger, you expect D times D dagger to be 1, the identity operator. So let's do that exercise here. Let's take the dagger. So that's easy. We just flip the sign of I everywhere. But here the operator involves the auxiliary field only living on the manifold. So you have to introduce a separate dynamical gauge field on the dagger operator as well. So you not only have little a, but you also have a bar. And now you fuse the two of them. This term just canceled. That's just saying that the classical axial rotation is unitary as we expected. But the rest of the terms don't cancel. And it gives you a non-trivial operator. It couples to a bulk U1 dynamical gauge field. It looks a little bit trivial, but it actually acts non-trivially on the operators in the theory. Yeah, go hard.
I actually forgot to ask you about this.
Yeah.
Now that you added little a on the world volume of this topological charge, there is an extended Hilbert space. So the Hilbert space of the theory now includes also the states that come from the fractional quantum Hall state.
No, Which Hilbert space though?
Little a, because now Wilsonize of little a act on the vacuum if you took the full space time to get
No, but you can prepare this operator at a fixed time.
Yeah.
Right. And you quantize your theory somewhere else at a different time. That Hilbert space doesn't see little a.
But if I put it parallel to time, then you have a new Hilbert space.
Right. That would be a twisted Hilbert space, but I'm not talking about that Hilbert space at this point.
Should we just regard the integral over little a as part of the definition of the operator?
Yes. Yes, absolutely.
I'm just asking about what dagger means. If you've extended the Hilbert space in the defect sector, then you're not acting
excellent. So here I pretended it's an operator at a fixed time acting on the ordinary Hilbert space of QED. Now, and as an operator, I can take the dagger. More generally, when M is a general manifold in the four-dimensional Euclidean space-time, dagger should be replaced by the orientation reversal. And there's a very precise definition by what we mean by orientation reversal.
But in certain sense, look, when you're saying that conjugation change A to A bar, then I would say that the original operator is not Hermitian. In the exponent is not Hermitian operator, right? Because
the exponent is not a good operator, indeed.
Yeah, right. So then
the exponentiation is. There's no charge for this symmetry.
Then it's not unitary.
It's not unitary. That's the whole point. That's in the title.
Okay, you have 15 minutes.
10 minutes?
15
minutes, okay.
So you're kind of showing that you sacrifice something in addition to being topological.
But let me
sacrifice the different Hilbert space interpretation.
But let me just say, in Chern-Simon theory, ADA, the charge conjugation symmetry operator takes exactly the same form, but you don't make the same complaint there.
No, but I think it's different setup.
It's different setup, but both involve an auxiliary field on the operator.
No, but usually in QFT, we like to be able to put charge operators parallel to time.
I could do that here as well.
That extends the Hilbert space. Then
that's always the case. Take any defect, you twist the Hilbert space, that gives you a defect Hilbert space. It's not, yeah.
Why is the operator non-trivial?
Oh, sorry, say again?
I mean, you can even integrate out the little a's.
I actually couldn't integrate out little a on a general three manifold.
I understand you cannot, but if I naively do it, it seems that the operator you get, the C operator is trivial. Is it too naive?
That's correct. So if you choose your space to be R3 non-compact, then you can integrate out little a. And indeed, the C operator on non-compact space acts trivial.
I guess you're going to explain why it's being trivial.
How many slides do you still have?
15.
Okay, then stop discussion.
Okay.
Do it.
Okay, yeah. I'll be happy to talk more at the break. Yeah, but I think I'm good inclined. I'm halfway through, and you say I have 15 minutes left, right?
15 minutes, yes.
Okay, all right. I can get it through. All right. So you fuse D with D dagger, you get the operator C. This C operator looks almost trivial, but it's actually what is called a condensation operator in the recent literature. And for the condensed matter physicists, it's actually a generalization of the Cheshire string. That's commonly studied in discrete case. But let me not say too much about C. The whole point is that C is not 1. So D times D dagger is not 1, and it's therefore not a unitary operator. And that's why we call it a non-invertible operator. The operator D doesn't have an inverse. Okay.
Say if you have this C, can you take a square root of C or whatever and to define unitary operator? Can you still, multiply original D1 over N by something?
In the case of one flavor QED, no.
Yeah.
No. But in other cases, we could. Okay, so we can also generalize this operator for general rational number. You just replace the U1 level N Chern-Simon theory by what is called the minimal TQSD. It's labeled by 2 integers now, N comma P, and they're co-primes. I'm not going to say too much about these more general operators, but it can be done. So the upshot is that the continuous invertible U1 axial symmetry is broken by the ABJ anomaly to the discrete non-invertible global symmetry labeled by the rational numbers. However, the group multiplication law of this operator is not the group multiplication law of the rational numbers. It's something more subtle. So here's a score list. We start with this operator. It's gauge invariant but not conserved. And this guy is not gauge invariant, it's conserved, it's invertible. And now we end up with the last one. It's gauge invariant, it's conserved, so that's great. But the price we pay is that it's non-invertible. But we should learn how.
But you still have arbitrary N. So for each N, it's a new series. I mean, like
no, it's a new operator. For
like but it's the same series.
Same theory, same QED. In the bulk, it's the same QED, electrons, positrons, photons. All right, now coming to the question that you asked earlier. So why should we think about this non-invertible symmetry as a global symmetry of the quantum field theory? This question echoes with the recent development of what is of generalized global symmetries in high energy physics and also in condensed matter physics. So in one of the first slides, we talk about how an ordinary global symmetry gives you a topological operator in Euclidean space-time. So every ordinary global symmetry is associated with such a topological symmetry. But then it's natural to ask the converse. If every topological operator in a given quantum field theory associated with the ordinary global symmetry? And the answer is not true. And those topological operators not associated with any global symmetry will be called a non-invertible symmetry or non-invertible topological operator. And in these two papers, it was advocated that this more general non-invertible topological operator should be viewed as a generalized global symmetry. The simplest example of such a non-invertible topological operator is the Kramers-Wanier duality line in the 1+1 dimensional Ising-conformal field theory. In that case, you can set up this line in your two-dimensional space-time to bring the local order operator, which is a point in space-time, past this line, it becomes a disorder operator. The disorder operator is attached to a Z2 branch cut. So it maps the local operator to a non-local operator. And that's the hallmark of being non-invertible. Here are some arguments that this non-invertible topological operators qualify as generalized global symmetry. First of all, some of them can be gauged just like the ordinary global symmetries. There's a generalized gauging procedure. Second, when there's an obstruction to gauging such a non-invertible symmetry, they lead to generalized to Hoof anomaly matching condition, and that gives you non-trivial constraints on the renormalization group flows. And third, in quantum gravity, it's usually believed that there's no global symmetry, and that conjecture is recently argued to be generalized to the absence of invertible and non-invertible global symmetries.
But these operators do not form a group, if I understood
correctly. They don't.
Yeah, but if they do not form a group, then it is not symmetry by definition of symmetry.
Oh yeah, I mean that you can take that as a definition, but here we take a
but then you should not call it symmetry.
I mean, if you hate the word symmetry, I can take it out. Yeah, but I'm going to tell you the fun thing about this topological operator. It's up to you to call it a symmetry or not.
Yeah, but avoid confusion because all people keep in mind what means symmetry.
Yeah, it's a generalized symmetry.
Conservation law.
It's conserved. It's topological.
But in what sense you use the term non-invertible? Non-invertible, the word non-invertible refers to which part of this?
Oh, non-invertible means that if you take this operator D, there isn't another operator D inverse such that D times D inverse is 1.
I see. Okay.
Yeah.
I see.
And for a group-like symmetry, that will always be the case because just take the inverse group element. And indeed, I completely agree with you. In my first paper, I call it the non-symmetry line. But over the years, I changed my mind. I think it should be viewed as a generalized symmetry. But I think that's how physics progresses. Right? We have some ideas A, and we find a new thing X, and X doesn't fit into A. But later on, we realize that X should be viewed as a generalized A.
But you should avoid confusion because
it's okay. It's okay. If you hate that word so much, just call it topological. Yeah.
Now in the modern world, people rename things all the time.
Yeah. I was on your side a few years ago, but now I changed my mind. Okay, let me continue. Yeah. Okay, so in the past year, there has been a lot of developments on the construction of non-invertible symmetry in familiar 3+1D lattice and continuum gauge theories. So this is a list of references that happened in just the last few months. These examples include the free Maxwell theory for the n equals to 4, etc. This construction to apply to quantum field theory that are invariant under gauging a discrete one-point symmetry. And the construction goes as follows. You start with a general quantum field theory with a one-point symmetry G. You gauge the symmetry only on half of the space-time. And you impose a Dirichlet boundary condition for the discrete gauge field. Generally, this gives you an interface between quantum field theory and its gauge version. But in the case when the gauge theory is isomorphic to the original quantum field theory, this gives you a defect in the single quantum field. And this is how a lot of these non-invertible symmetries in 3+1D arise.
5 minutes.
Okay. So now let me give you alternative construction for the operator D in QED, which we talked about. In QED, I'm going to assume there's no monopoles. When there are, that's extremely interesting. That's actually discussed by Clay and Cantaro in the paper last night. But when there's no dynamical monopoles, there's a magnetic U1 one-point symmetry, whose current is just star F. The conservation of the magnetic symmetry is just the Bianchi identity. The charged objects are the two hoop lines. Now you can show that by picking a Zn subgroup of the U1 one-point symmetry, and you gauge it, then what it does to QED is to shift the theta angle by this rational amount. But in QED, we know the theta angle is not meaningful. You can always undo it by an axial rotation. So that means by composing the gauging of the Zn one-point symmetry and an axial rotation, you can actually bring the QED back to the original theory. So QED is invariant under these two operations. And therefore, you can construct such a topological operator by doing this gauging and axial rotation only in half of the space-time. And since the theories on the two sides are isomorphic, this gives you a topological defect in the single theory. For discrete gauge theory, the Dirichlet boundary condition is topological. So this defect is actually topological. And that's a rigorous proof why the operator D is topological. I'm using the word operator and defect interchangeably because I'm always in Euclidean signature for a relativistic on the field. And from this gauging construction, it's also clear how it acts. When you bring a two-hoof line past the defect, it experiences a gauging of the magnetic one-point symmetry. And since the theta angles is shifted by this amount, by the Witten effect, we know the two-hoof line acquires a fractional electric charge. But the fractional electric charge is not a genuine line operator. It's actually the boundary of a disk. So it maps the genuine line operator, the two-hoof line, to a disk operator. And the disk operator is just a fancy name for a two-hoof line carrying fractional electric charge. This picture is supposed to be compared with the action of the Kramers-Wagner duality line on the local order operator. It takes the order operator to a disorder operator. On R3, as noted earlier, this operator reduces to the naive U hat operator because there's no large gauge transformation on R3 for U1. That's the statement that there's no instanton in flat space for U1. And as Alexi was saying, rational numbers are almost as good as U1. So the selection rules that this non-invertible symmetries leads to are basically just the naive selection rules of the U1 axial symmetry. And what do they mean in massless QED? It just means that the total helicity of the electrons and positrons has to be conserved in scattering amplitudes of massless QED, but not the photons though. So for example, if you consider electron-positron annihilation, the helicities of the electron and positron have to be opposite. Otherwise, the scattering amplitudes vanish. This is a very familiar fact that I learned in chapter 5 of Peskin and Schroeder. Let's take a look how it was proved in that textbook. It was proved using the gamma 5 matrix, which is essentially correct because gamma 5 is tied to the U1 axial symmetry. But Peskin and Schroeder didn't dare to say that there's a symmetry reason for this fact because the U1 axial symmetry down the road will be broken by ABJ. But now that we understand, it can actually be understood as a non-invertible global symmetry. Anyway, this is just an extremely fancy way to understand something we learned in the first few chapters of quantum field theory textbooks. All right, so let me just quickly go through the QCD example. Let's consider QCD below the electroweak scale. So the SU2 times U1 is already broken to the U1 electromagnetic gauge symmetry. And I'm only going to look at the up and down quarks. There's a U1, classically, there's a U1 global symmetry acting on the U and D quarks by this rotation. It involves a gamma 5 and a sigma 3. This classical global symmetry suffers an ABJ anomaly with the electromagnetic U1 gauge symmetry, and that was the origin of the ABJ anomaly. By the exact same construction, we conclude that there's an infinite non-invertible global symmetry D in QCD. Now the question is, how does the pion Lagrangian capture this non-invertible symmetry? We have this symmetry in the UV QCD. How does it manifest itself in the pion Lagrangian? The terms we're going to look at in the pion Lagrangian are these two terms. Here, this is the neutral pion. It's a compact scalar field. And I'm going to assume there's a coupling pi 0 FF with some coefficient G. For all I know, G could be 0 at this point. But I'm going to claim that for this Lagrangian to realize the non-invertible symmetry in the UV QCD Lagrangian, it actually has to fix G to a very specific value. The way it works is that you insert this defect, this operator as a defect, say at x equals to 0. So that's kind of what Zohar was pointing at earlier. You insert this as a defect, and in the bulk, on the two sides of the defect, you have the bulk pion Lagrange. And now you just solve the equation of motion for this combined system. You have an equation of motion for the pion field, you have an equation of motion from the little a living on the defect, and you have an equation of motion for the bulk capital A U1 gauge field. There are three equations, and you can easily show that the only way these three equations are compatible with each other is that this coupling between pi 0 and FF has to be fixed to this very particular value. So conventionally, the pi 0 FF coupling is explained by the ABJ anomaly. Here we give an alternative derivation of this coupling as a direct consequence from matching the non-invertible global symmetry in the UV.
Where is NC in this discussion? Isn't there an NC in that coupling?
Oh, yeah, it has already been simplified. I mean, this coefficient already contains that NC.
But where did it come from? I mean, in this gauging procedure, how does it know about NC?
Yeah, so it doesn't see it explicitly because the starting point.
I'm sorry.
The starting point is just the anomalous conservation equation, which already comes.
Minutes.
Okay, all right.
Never mind.
I'm almost done. Yeah, I can say a little bit more later on. Yeah,
I'll ask.
Yeah, you even have a footnote explaining how that works. All right. So yeah, so the non-invertible global symmetry, all these D's, give an invariant characterization of the ABJ anomalies in the assuming there's no monopoles, and it explains this pi 0, the neutral pion decays in terms of the existence of a generalized global symmetry rather than the absence there. Perhaps the pion field, the neutral pion field, can be viewed as a Goldstone boson for the non-invertible global symmetry, but I have to put the Goldstone boson in a quotation mark because the symmetry here is actually discrete. But again, it's labeled by rational numbers, so it's almost like a continuous symmetry. And perhaps that's the reason why the neutral pion is so light at the same time emitting a non-derivative coupling with the F wedge F. All right, okay, I can skip this slide. This is about general construction. Let me jump to conclusion. So what we concluded is that in massless QED and QCD for the real world, the continuous invertible U1 axial symmetry is broken by the ABJ anomaly to a discrete non-invertible symmetry labeled by the rational numbers. The non-invertible symmetry operator is a composition of the naive axial rotation with a fractional quantum Hall state. It can be realized by gauging a discrete subgroup of the magnetic one-form symmetry in half space-time. And that's why the absence of monopole is essential for this construction. And please see this paper from last night for discussion on what happens if these symmetries are broken by the monopoles. So to put it in a maximally offensive way, this is the alternative way to understand why the neutral pion can decay into photons. In my last slide, let me just show you, I made a little timeline for the development of non-invertible symmetries. So I think the first place where non-invertible symmetry appears is in 1+1D integrable system. There are all these topological lines obeying the Young-Baxter equation. And then in the late 80s, there were all this wonderful work on rational conformal field theory, where the non-invertible lines in 1+1D RCFT make an implicit appearance. And then there are a lot of development in the middle, starting from around then, it has been recognized that these non-invertible lines in 1+1D should be viewed as some generalized global symmetry. And then there were a lot of construction in the real world 3+1D, well, in 3+1D gauge theory just last year. And now we realize that there are also non-invertible symmetries in nature, and we'll see what happens. Thank you very much.
Okay, thank you. Okay,
yeah.
Please.
So do you have any particular experimental experiment that can be done that will show a difference between predictions, the formal predictions of these new ideas versus the old?
Not yet. Yeah, it would be disappointing if this is the last paper on the subject, but I hope there will be more we can discover.
So far, you didn't.
So far, it's a post-diction. We post-dict that neutral pion should decay into two photons.
Let me make a very short comment.
Yeah.
If I understood correctly, but I didn't see any new insight. You narrow from real symmetry, from real group to something let's call it discrete.
Yeah.
But you do not give any new insight as compared to original symmetry version.
Well, in this particular context of pion decay, yeah,
no new physics insight.
Well, in the previous work which I kind of gloss through over here. There are a lot of new constraints you can get from the non-invertible symmetry. Here, as I said, it will be disappointing if this is the last paper on K+1 physics. Yeah.
If you will find new insights, it will be really very
yeah. But in other dimensions, there are many new insights here, new constraints that you wouldn't be able to obtain otherwise.
Okay, thank you very much.
Thank you.
So, you on the bottom, if I pronounce name correct.
Oops.
Well, because I've been thinking about that for years. Because you see, this, I mean,
Some
as I said, it's really disappointing. The last paper I was talking about. I'm not going to retire after this paper.
It's not neat.
which time?
I don't understand. You see the
Will come from the easiest is from the hotel, no?
It's what we have time. Okay, it was a question.
I say
anyway, I need to become my wife.
Okay, so please begin.
All right. Thanks. So, so my name is Fiona Burnell, and I'm from a condensed matter background. So I'm going to tell you guys about something a little bit different that hopefully will interest you, about subsystem symmetry protected phases and their connection to anomalies and higher form gauge theories. So I wanted to start by connecting something that you all know and love, which is anomalies, to something that we care about a lot in condensed matter physics, which is basically the classification of different kinds of phases of matter. And so I'm going to start by giving you a very pedestrian kind of introduction to the interpretation of, everyone's favorite anomaly, the axial anomaly in condensed matter physics, and its implications for what we can say about different phases of matter. So I'm going to just start in 1D, so very, very pedestrian. And here is Lagrangian in 1D. We can think of it as a bosonization of some fermions, right? And so for us in condensed matter, this is a 1D metal, and typically it has a Fermi surface. And when I bosonize it, I expect to get some right movers over here at some momentum plus kf, and some left movers over here at another momentum minus kf. Okay. So what does the axial anomaly mean? Well, I have two conserved densities. Okay. One is just the charge density. And another one, this axial current density, again, from a condensed matter perspective, and I'll come back to this later, it's actually kind of natural to associate it with the momentum density, right? Because I can just multiply this number kf by this difference of, the number of charges over here minus the number of charges over here, okay? And then, as we all know, okay, so what are these two currents, right? So there's an electromagnetic current who, in this bosonized language, right, the density is just dx of phi, right, from bosonization textbook, and then the spatial current is dt of phi. And you can see that this current is just conserved, right, with this Lagrangian quality of mixed partial derivatives, nothing I can do. But there's another current, right, which is the axial current, and its density turns out to be, and this was this one that I can connect to a momentum current, and its density turns out to be proportional to dt phi, right? And then its spatial current is dx phi. And this one is conserved, but only due to the equations of motion. Okay. And so now, obviously, if I add a background electric field, I modify my equations of motion, and this axial current is no longer conserved. And from a condensed matter perspective, what that means is applying an electric field. I can think of that as putting, a gradient of the chemical potential between right moving branch and left moving branch, and I'm just moving some fermions from the left movers to the right movers through the Fermi sea. Okay, no need to do any diagrammatic calculations. Perfect. And so, you know, this boils down to something which is very familiar to us, which is in a one-dimensional metal, if I apply a magnetic field, you know, the momentum current is not conserved. Okay, so this is the condensed matter interpretation of a very familiar anomaly. Now, so the story that I want to tell is a little bit different from that. We'll come back to this picture at the end, but it's also the case that if I put this, you know, theory on the boundary of a two-dimensional system, and I write an appropriate bulk term that now, so this would be, you know, a gauge field corresponding to this axial symmetry, and this is my ordinary U1 gauge field, and I write down this mutual turn times theory in the bulk, right? So now this is not gauge invariant, but you know, under both of these gauge fields, but the boundary is also, you know, not gauge invariant under both of these fields, and so we get this cancellation of the gauge non-invariance of the boundary. And so now what we find, right, is that when I put a theory at the boundary of a higher dimensional system, these anomalies can be canceled. Now, this specific example is not one we think about a lot in condensed matter, simply because there isn't a natural physical interpretation of this axial gauge field, at least not one that we sort of talk about a lot. But there is a very famous analog of this, okay, which comes in the following context. So imagine that I just took away one of my branches, right, and I had a theory of only right movers. So as you all know, in this case, this is a terrible idea because we have a, you know, a gauge anomaly, and so if this is the U1 gauge symmetry, it's anomalous, and that's very, very bad. But of course, we can play the same trick. Okay, I can, you know, imagine putting this one-dimensional system at the boundary of a two-dimensional system. That two-dimensional system would have to have some kind of effective Chern-Simons theory in the bulk. Okay, and now this anomaly is canceled. Now, an interesting observation about this bulk theory, these are, you know, think of these as maybe classical response background gauge fields. It predicts a sort of interesting electromagnetic response in which the currents flow perpendicular to the electric fields. And in fact, this is something that was observed, you know, starting in the 1980s, that this really happens when you take, you know, you take a stack of semiconductors, you make a basically two-dimensional electron gas, you stick it in a large magnetic field, okay, and you get something called the quantum Hall effect. Okay, so this is a plot of, as a function of the magnetic field, the resistivity, you know, this which is telling me about how much current flows in this direction when I apply an electric field in that direction, and we see these quantized plateau. Okay, and so this phenomenon, which you could have, you know, thought about by just saying, well, where could I put my, you know, chiral boson with U1 conservation symmetry? I could put it at the boundary of a system that has this funny conductance property. You could have ex post facto predicted that there would be phases that have this quantum Hall conductivity. Okay. And so this is a very general sort of theme in condensed matter physics, that basically we like to think about anomalies in the context of using them to classify interesting bulk phases of matter. So what's going on here is I have a boundary theory with a symmetry that's anomalous. Okay. Usually these are Toft anomalies. This quantum Hall theory is a little bit different from the kind of the most conventional examples in this class, if you like. But the symmetry is anomalous, meaning that it can't really be realized with the kind of on-site normal lattice realization. Okay, but it can happen at the boundary of a system. Okay, and now because there's an anomaly in the boundary that is canceled by some kind of anomaly inflow from the bulk. Okay, then this boundary is protected. That means that I cannot get rid of it. I can't gap it out. Okay, and that, by the way, if you come back to this picture here, you'll notice these plateaus are very well quantized. You can do a lot to these samples, make them very dirty. Okay, you still see this kind of quantized conductance, and one way to think about that is because these conducting boundary modes, you know, are very, very robust, even if you make the system really dirty, very impure. Okay. And so this is why we call these sort of symmetry protected gapless boundary modes. And another kind of famous example, which you've probably heard of, is the topological insulator. Okay, so here the anomaly is a discrete anomaly. It has to do with the fact that if you have an odd number of Dirac cones in 2 dimensions, you cannot also have time reversal symmetry. But you can if you put that on the boundary of a three-dimensional bulk with a topological theta term. Okay.
Excuse me?
Yeah.
So why don't you have this F squared term, E squared minus this?
Okay, good. Yeah, so I could add an F squared term. So the gauge fields that I'm talking about today, we're mostly thinking about, we want to write down a theory for the background electromagnetic response. So we're thinking, you should think of them as classical gauge fields. So if I could add that term, but then I would be talking about dynamical gauge fields. So I'm thinking about a situation where I'm in the lab and the electric and magnetic fields are something that I'm applying with, like light or magnets or something like that. And so we're just measuring what is happening to the charges in the presence of these classical background fields. And so that will apply to the kind of Lagrangians that I wrote down. Does that answer your question?
And in general, do you need a relativistic invariant one that you can take also non-relativistic for this condensed?
So yeah, so this is an excellent question. So the question for those who didn't hear is that, do I need to write down some kind of relativistic invariant in the bulk? And the answer, and we'll, so later in the talk, we will see the answer is no, right? So in condensed matter, I'm typically, microscopically, I have a crystal, there's a lattice, and there's no a priori reason that we should be committed to having relativistically invariant sort of topological terms describing these bulks. It just so happens that, most of the early ones happen to work out that way, and they map onto kind of anomalies that were studied in high energy theory. But yeah, we'll talk about that more. It's an excellent question.
But if you will add, say, E squared term, right? No, just E squared or B squared term, not using the relativistic invariance, right? With a bit coefficient, right? Is it important for you or it's not?
No. So again, so E dot B basically it does a couple of things. Okay, so it tells me basically what this E dot B term does for me is it tells me, and this, by the way, is an experimental image taken by ARPES, so photo emission spectroscopy. And so you look at the surface of this system and you see that there's an odd number of Dirac cones. However, you also see that there's no magnetic order or anything. There's no evidence of time reversal symmetry breaking. Okay. So what E dot B is doing for me is allowing my experiment, my material to actually have a single Dirac cone on the surface. Like same thing as, when people were doing, sort of trying to study like chiral theories on the lattice, right? And this was one of the techniques that was used numerically, was just to think about your theory as being at the boundary of a higher dimensional system. It's really the same phenomenon. Yeah. Okay. And so I should say, this is a long story. So these are, I've sketched kind of a couple examples of a very big family of things that we know about. So we now, have a lot of different examples of phases of matter that we can understand are distinct from each other on the basis of this anomaly thinking. Okay, so I've written a list. I'm not going to say much about them, but there's, this picture is extremely useful if we want to know, if I keep the symmetry in a material, is phase A adiabatically connected to phase B? Okay, good. And so that's the kind of general philosophy of how, why we like to think about anomalies in condensed matter physics. And what I want to focus on for the rest of the talk is this, sort of, what do we get when we go beyond, if you like, ordinary global symmetries? Okay, so, things like time reversal, charge conservation. Because in condensed matter, we don't usually get a lot of non-abelian symmetries. So our range of ordinary global symmetries that we believe are relevant to real materials is pretty limited. So what do I mean by beyond ordinary global symmetries? Well, the examples that I'm going to focus on today. So an example that you might think, and I will argue can be physically relevant for materials, is a system which has a conserved dipole moment. Okay. So the overall symmetry is U1, but it has not only a conserved U1 charge, but also a conserved U1 dipole moment. And for much of the talk, I'm going to focus on examples with what we call subsystem symmetry, which is kind of like dipole moment conservation on steroids. And I'll explain a little bit more why that is later. But let me begin by motivating, why would you go beyond, say, charge conservation? What's the reason for this? So one big motivation for this is comes from an alternative way of describing topological phases of matter for non-interacting electrons. And so, you know, if you go back and you read the condensed matter literature on topological insulators, you'll find that people can classify these phases of matter by calculating something called, you know, topological invariance of what we call the band structure. Okay, so basically the way that the energy, the eigenstates of the Hamiltonian change as a function of momentum in the Brillouin zone. Now, a few years ago, there was a very nice paper by Ben Alcazar, Bernavig, and Hughes, and they observed that using that kind of method, okay, thinking about the topology of band structures, basically, if you have a filled band with net zero dipole moment, okay, you can have other topological invariants. These have to do with the quadrupole moment of the system. And in the presence of crystalline symmetries, these can be quantized, and you get actually basically a completely new kind of phenomenon. So if this is like the topological insulator, okay, so the gold just means I have a gapless mode in this region. So, you know, Dirac cone on the surface. If I have a quantized quadrupole moment, what I can see is gapless modes running along the edges. Okay, quantized octupole moment can give me little gapless guys, okay, little degeneracies living at the corner of the cube, okay? And so if we think about, you know, things like conserved dipole moment, we know in band theory that there is something out there that is beyond what we already know.
Sorry, are you saying that if you have a sphere for the boundary, then there would be no effects from it?
Yeah. Yeah, basically, yeah. This cares about, you know, kind of the geometry of the system in a way that, say, a topological.
Examples of this type appeared also in high energy physics before, that if you take the boundary A and the boundary B, and they intersect not smoothly but with an angle,
yeah,
then there are some modes localized at the angle.
Yeah,
there are many such examples.
Yeah, right. And so this is a statement, and you know, and I should say that you know, there are materials now that people, you know, look at to find these things.
No, but still the kind of physical reasoning for the symmetry, I don't know, for example, Dipole model, how it could be, for example, associated with spin, for example, in TV6 theory, that you have something associated with spin which kind of protects it, right? Because no, like on non-invertible particle, you have spin decouple, you know, then you can have conservation associated with spin. And it is in this way kind of analog of dipole, right? So when you are saying that there is this conservation of quadrupole of dipole, I still would like to see, you know, what kind of conservation law is related.
So yeah, so I should say that in these systems, so I will you know, give examples where we have, you know, an exact conservation law at the lattice level, but in these systems, it's actually, you know, these are, oh my goodness. These are systems which are, you know, free fermions, okay? And so they're not, you know, it's not that the Lagrangian microscopically conserves the dipole moment, but the fact is that the you know, you then look at the low energy theory, so you have kind of a band of filled states, if you like, and in that band, the net dipole moment is 0, and then you can talk about higher.
I see. So it's like an integrable system, right? In certain sense, where you have extra moments which are conserved.
Yeah. In that sense, yes. And I should say here, you know, it's a charged dipole moment, not a spin dipole moment. Yeah.
So you cut the system with a boundary. Does the presence of the boundary break the dipole symmetry?
It can, right? So
sometimes like in many cases, the dipole symmetry is realized by shifting the field linear in X. So if we cut it somewhere, what does that do?
Yeah, so like the simplest example is, you know, let's go to 2 dimensions, and then so you have sort of no dipole moment in the bulk, and then what happens at the boundary is you get a sort of a polarization along the boundary, so a charge polarization, and then at the corner you get these gapless modes. So yeah, like in the bulk, the statement is there's no kind of net charge polarization, and then that polarization appears at the boundaries, and then the way those 2 polarizations intersect is as if you had, you know, a single boundary of a one-dimensional kind of topological insulator.
But that doesn't the boundary just break the symmetry explicitly?
So the symmetry, In terms, yeah. So the symmetry here involves some lattice symmetries as well. And so really the statement is that you need the you know, in the absence of a boundary, you need the net dipole moment of the band to be 0, and that's necessary. So in this classification, that's necessary because otherwise you can't talk about the quadrupole moment being well defined. Once the quadrupole moment is well defined, you can look at the bulk and you can ask, you know, are there kind of different kinds of quadrupole moments? And the answer is yes. And then for those different kinds of quadrupole moments, you know, you can cut the system open, you get this boundary polarization, and then you find these corner modes, and they're actually protected by a lattice symmetry. So it's a little bit sort of more involved than just dipole symmetry.
I see. It's not like in the SPT case. There are no light modes on the boundary everywhere, but just at the edges.
Yeah, exactly. Yeah, and it's exactly like you said. You should think of this as kind of defects between different kinds of boundaries, and they have these extra gapless modes. Yeah. Okay. And so, you know, we might like to understand, and I will not achieve this goal, but, you know, we might like to understand, you know, this kind of picture completely in terms of anomaly inflow and what is the full classification of these kinds of anomalies for interacting theories and so on. So we won't get there, but let me tell you about a couple of things that I think, you know, get us working in this direction. So I'm going to begin by giving, I'm going to focus on one example because we don't have too much time of an anomaly in a theory with subsystem symmetry, which is a stronger version than dipole conservation. Okay, and I will then come back to some connections. So I'm not going to say very much about this higher order about connections to higher order topological insulators in this talk. You can ask me about that afterwards, but, you know, there are some connections also between different kinds of subsystem symmetry and higher order topological insulators, but I'm going to connect this back to a you know, more pedestrian physical system at the end. Okay, so let me begin by telling you what is subsystem symmetry, right? So subsystem symmetry is kind of like, it's like a one-form symmetry where you commit to a particular set of direct, you know, lines in the lattice or submanifolds. Okay, so here's the first picture is basically I have an independent symmetry generator. I pick a lattice, I have an independent symmetry generator, and it can act along, you know, say in this two-dimensional lattice, any line in Y or any line in X. Okay, and if I draw a three-dimensional system, I have lattice planes, and my symmetry can act independently along families of those lattice planes.
Are these the same symmetries acting along X?
Yes. Yes. Yeah. So let's take a concrete example. Let's imagine that the symmetry is a charge conservation symmetry. And so what this would mean, so, you know, independent U1 rotations along here and here and here, okay, means that the charge is individually conserved along each of these lines. And so what that means is that an individual charge, so this is why it's like dipole conservation on steroids, an individual charge is just immobile. It can't move at all because if it does so, it's going to violate charge conservation on some of these lines. However, if I make a dipole, right, so red will be positive charge, blue will be negative charge. Now this dipole can move, but only perpendicular to the direction of its dipole moment, okay? So it's like dipole conservation, but it's much more restrictive. Okay. And since we're going to talk about response theories, I should also tell you, you know, give you kind of a basic picture of how to gauge these symmetries. So there's the kind of the first paper to talk about how you gauge these was from sort of 10+ years ago by Vijay Ha and Fu. But the point is that when you have this kind of subsystem symmetry, the natural way to gauge it is to introduce a gauge field, if you like, on the lattice. We think of it as sitting at plaquette centers. Okay, A naught sits at the edges. And the reason that it's natural to put this guy here is that we want its gauge transformations to be different, okay, than the usual gauge transformations that you're familiar with for a vector gauge field. Why is that? Because this gauge transformation implies the following current conservation law, okay? So this is dt rho is, so rho is my charge density, J naught, okay, is dx dy, jxy, I just have a single component of the current. And what this means is that if I, you know, integrate the right-hand side along, let me put the system on the torus, I integrate the right-hand side along any line in the x direction, any line in the y direction, and I find that the total charge along each of these lines is conserved. And so that's why you should think of this as the correct, you know, sort of gauge version of this symmetry.
This doesn't conserve dipole moment, right? Because you could still take the plus and minus and make them very far from each other as long as they're on the same line?
No. So the dipole can only move perpendicular to its
But
dipole.
the dipole moment is not conserved because you can take the plus and minus very far from each other.
No, I can't. Right. So I basically have to.
The red thing can go up and the blue thing can go down, and the dipole moment will increase.
No, it actually. So the red thing could go up if I put a minus here, and then it can go this way.
Like some red and blue cannot interchange while sitting on the same.
Yeah, because so if I just move the red this way, right, then the charge along this line is not conserved.
Oh.
So it's the fact that I have charge constant that this.
You have on both lines.
Yeah, the fact that it's on both lines is what's doing that for me. Yeah, good. Okay, and so that's subsystem symmetry, and so now if we want to kind of understand maybe the new options in terms of symmetry protected phases of matter, a natural thing to ask about is, can we find analogs of familiar anomalies, and can we identify bulk theories that would cancel these anomalies? And so the answer is yes. Okay, and I'm going to so we have several examples about this in this paper here. I'm just going to tell you about one of them, and then I'm going to tell you a little bit about how the anomalous boundary is reminiscent of something that we see in much more kind of experimentally realistic solid state systems. So let me tell you about, so we talked about our favorite anomaly, the axial anomaly in 1D at the beginning of the talk. So let me tell you about the analog of that theory. So here's a Lagrangian for, so the axial anomaly, we started with a free boson in one dimension. Here's the Lagrangian for a free boson with subsystem symmetry. So it looks exactly like my free boson in one dimension, except now it's living in two dimensions, and instead of just dx phi squared, I've got dx dy phi squared. Okay. Now this theory is unusual. So this is definitely not relativistic, right? Because I have, if I look at kind of the dispersion relation of this particle, anytime either kx or ky is 0, I have these lines of 0 energy states. Okay. So very different from what you're used to thinking about in the relativistic context. But we can see that this has a subsystem symmetry. So in this case, we would want to think about phi as, the phase of some field. Okay. And this, and you can see now that because it's dx dy of phi, that I could shift phi by any function of x that I like, plus any function of y that I like, right? And this Lagrangian will be invariant.
You have 10 minutes.
Yeah, I think that should be good. I think I'll even have some time for questions at the end. Okay. Good. Okay. And so, yeah, so right. So I should say that, the one thing that you have to be a little careful of is that, having a cutoff in energy is not the same as having a cutoff in momentum. And so, if you wanted to think about this momentum, if you wanted to think about this not on a lattice where momentum goes on forever, then you have sort of extended lines of 0 modes. All right. So just like in our 1D axial theory, this system has two classically conserved currents, right? One has the charge density being associated with, in this case, two derivatives of phi, right? So you could think about this as a kind of dipole charge density, if you will. And the other of which the spatial current has dt phi, right? And this, again, is conserved just by equality of mixed partial derivatives. So this current is conserved. Yeah.
But does this theory actually make sense? It seems like if I put it in compact space, it has infinitely many ground states.
It does. Yeah.
Does it actually make sense?
So
I just put kx to 0, then any ky gives you 0.
So he's complaining about the fact that I have many 0 energy states.
Yeah, but those classical 0 modes are lifted from the mechanical.
Quadratic theory.
Yeah, but it's just like in compact boson in 1 + 1d. You have 0 mode. That 0 mode will be lifted. That's the main point of the classically you see all these light modes. So you quantize it, it's quadratic indeed, but they become simple harmonic oscillators. And then the vacuum energy of the simple harmonic oscillator. Another way to say it is that the charge states on the global symmetries Fiona was saying are actually infinitely heavy. That's right.
So maybe we can talk more about that after. Okay, so I have this conservation law, and then once again I have a second choice of current. Okay, whose charge is just dt phi, and then whose spatial part is dx uy phi, and this guy is conserved due to the equations of motion. So as you might expect, if we take our higher rank gauge field and we add, you know, a kind of so we add the analog of an electric flux. Okay. Then what I find is that the equations of motion get modified. Okay, so EXY is the electric field associated with the gauge field AXY. Okay, and the equations of motion get modified, and this second current is no longer conserved. Okay, and so, you know, again, if I thought of this as a theory of dipoles, there would be a kind of cartoon interpretation. In fact, there's two cartoon interpretations. I could think about, you know, a system in which I have a dipole in the y direction, and I have right movers and left movers in x. Or I could think about my dipoles being in the x direction and having, you know, right movers and left movers in y. Turns out that if you actually look at the pattern of charge mobility, these two are equivalent, which is, I think, the way to understand there's only one current. And in either case, when I apply this sort of higher rank electric field, what I'm doing is just, you know, moving left moving dipoles to right moving dipoles. Okay. All right. And so now, okay, so now we have this, you know, sort of anomaly, which is of a higher rank nature, and we can see that it, you know, we could think about it as telling us something about dipole transport. And then, you know, if we're interested in classifying phases of matter with subsystem symmetry, and you could argue about whether that's a physically relevant thing to do, but you can do it, okay? Then you would like to write down some kind of bulk action that's going to cancel the anomaly. Unsurprisingly, this bulk action, you know, has the character of a mutual Chern-Simons theory, just as it does for the 1D axial anomaly, okay? And I should say that, so here, you know, the subsystem symmetry is only along these sheets that intersect the surface. So, you know, the XZ and YZ planes here, and then my surface has lines in X and Y. So the surface is at Z equals 0. And so you can easily check that, you know, kind of clear, it's a Chern-Simons like term. This action is gauge invariant only up to a boundary term. And you can actually check explicitly that this term cancels the boundary anomaly. So this is a kind of anomaly inflow type picture.
But this does not have the feature that we explained before, that the edge modes are only localized on like edges or lines. Here it seems to be gapless everywhere in the boundaries.
Yeah, yes, that's right. That's right. This is not a hinge state. Yeah, this is not a hinge state. This is a kind of different beast. But let me tell you something that I think is amusing about these. So you can ask, because, you know, look, at some level I've got these kind of lines in the surface, and I've got, you know, protected gapless modes going along these different lines. And you might ask yourself, well, isn't that kind of like taking like stacks of lower dimensional systems, 2D systems that have gapless boundaries, and sewing them together, right? Isn't that just what you've written down? And so one concrete way to ask that question is, can I take some 2D systems and sew them together and kind of like glue them in here such that I kill this gapless boundary? And the answer turns out to be no. And let me give you kind of the flavor of that answer. There's a very nice paper by Trithep Devakul, Dominic Williamson, and Juven Wang, where they talked about classifying, you know, these kinds of phases with subsystem symmetry. And they arrived, so they did this very much on the lattice. They don't have a continuum field theory, but they arrived at the following picture that basically, so I'm going to say some words, and you know, for those of you who aren't familiar with them, you might have to talk to me afterwards. But basically, the protectedness of the gapless boundaries, you could describe it in terms of a group cohomology of the symmetry group. Okay, and so these diagrams are basically telling you, it's a pictorial description of which elements of this group cohomology are non-trivial. Now, if we take stacks of lower dimensional systems with the same symmetry and glue them in there, what you can see, perhaps unsurprisingly, is that the groups of these, the group cohomology, that's sort of non-trivial, lives in these localized clusters, okay? And they showed that, there are examples where that's not true, okay? For these subsystem symmetry protected phases, where the group cohomology, the non-trivial group cohomology sort of chains through the whole system, okay? And this is your signature so this sort of chaining through the whole system is your signature that this didn't come from just like gluing in sort of chunks of lower dimensional systems, because it doesn't break apart, okay? And so maybe the last thing I want to say about this is that, so perhaps unsurprisingly, the continuum theory, okay, that we wrote down actually captures only, so you could think about a coarse graining procedure where you kind of start lumping these sites together, okay? The continuum theory only captures the part of this kind of non-trivial group cohomology that's invariant under such a coarse graining picture. And so these field theories actually describe something that you couldn't make with lower dimensional systems. And so since our chair is standing up, let me just very briefly say a couple of words about something that amuses me, which is that there is a context in real materials where you see not this bulk theory, no subsystem symmetry, but a surface anomaly that's very similar to the one that we described there. And so here's a sort of picture of a Fermi surface, okay, which has the same sort of set of gapless modes as the bosonic system that we wrote down, and this conserves charge and momentum in both directions. It's a Hamiltonian for free fermions, okay? But what you can see is that basically if you apply an electric field, okay, so these are right movers in the y direction, left movers in the y direction. So if I apply an electric field in the y direction, this system fails to conserve momentum in the x direction, okay? And so this is an example of a fermionic system that you might write down with this same kind of Fermi surface. There is an anomaly, and in this case, it maps onto a non-conservation of a momentum current. Can you cancel it with a bulk? Well, one way to cancel it with a bulk is to put it on the surface of what we call a vial semimetal. So this is kind of an interesting class of vial semimetal where the vial cones are distributed in a quadrupolar pattern. Okay, so sorry to rush that, but maybe just to say, the kind of big picture is in condensed matter, we're very interested in different classes of anomalies. They tell us about different phases of matter. When we go from global symmetries to these sort of stronger global symmetries, including subsystem symmetry, we get these new classifications with things that are intrinsically not relativistic in this case. And some of these anomalies, even though subsystem symmetry is not something you would naturally expect in a material, have some sort of reminiscences in much more conventional material systems. And I'll stop there.
I have a question about the hinge states or the corner states that you showed.
Yeah.
So two parts. So first of all, are there parameters in the theory that you could vary where you could go from a system where you have a bunch of hinge states to you don't have any? And if that's if you achieve this, is there a phase transition between the two cases in the bulk?
Yes, perfect. Yeah. So the question is, what's going on with these hinge states? Can I tune some parameter to get rid of them? And if so, is that associated with a bulk phase transition? So the answer is yes, there's a parameter that you can tune. And the statement, and this is true for all, anytime you hear the word symmetry protected phase of matter, if you break the symmetry, the relevant symmetries, and here in these cases, lattice for these hinge modes, these higher order things, lattice symmetries are typically involved. Unless you have subsystem symmetry, but okay, then you don't need lattice symmetry. But basically the statement is this: if you preserve the symmetries, you cannot get rid of those hinge modes without going through a phase transition. So you can get rid of them. And so, like there are explicit Hamiltonians where you can tune some kind of parameter, some kind of mass parameter analog, okay? And you can go through a phase transition between a phase which has the hinge modes and does not have the hinge modes, but provided that you do that in a symmetry preserving way, the bulk must go through a phase transition. And so that's why we say symmetry protected topological. And that's where quantum Hall is different. There, you can't get rid of that edge mode without, going through a phase transition, no matter what, right? So yeah.
Fiona, when you say you preserve the symmetry, do you mean you preserve the symmetry in the bulk or also on the boundary?
Right. So yeah. So let me say the following thing about so suppose that I have, let me just draw the 2D case. Okay. So the 2D case would be, I have some, gapless mode, like spin a half here, spin a half here. So what can I do if and then, maybe I have some reflection symmetry here and reflection here. Okay. So what can I do if I break this reflection symmetry, but I preserve, the other symmetries, charge conservation and so on. So the reason that lattice symmetries are important is what I could imagine if I break the lattice symmetry is I could imagine making some kind of deformation. So I could take a one-dimensional topological insulator here, right? And I can glue it here to gap out this mode, right? So something with a free, say, spin a half. Maybe it's a Haldane chain, okay? Free spin a half at the end here. And I can do another one here. And then I can kind of move these guys along so that the edge modes kind of meet in the middle, right? So or another way to think about it is this mode that lives at the corner is actually the same. It's this. You could make that mode at the boundary of a one-dimensional SPT, right? But reflection symmetry means that if I have reflection symmetry and I glue a one-dimensional SPT here, I must also glue one over here. Okay, so that's the sense in which the lattice symmetries are important. Is that what you're asking?
So in this example, it's the lattice symmetry that protects
yes,
the gap.
It's the lattice symmetry.
Not some dipoles.
Yeah, that's right. Yeah. So the dipole conservation in these systems is used to classify the bulk topological invariant, but it's not a microscopic symmetry of the Hamiltonian.
I see.
Yeah.
If there is a very short corner of question, please ask. Otherwise, we will go for in that question. If not, thank you very much for.
Yes.
Oh, thank you.
Okay, I hope oh gosh, I'm sorry.
The level of the strong so the level of the strong interaction is
because there's no way.
You can on the plane structure.
Right. Then say, for example, charge fire became because they become massive. But but then just at your level, when you're introducing this kind of symmetry, I would say that the still so in this way, my theory is still
of my symmetry. I was because the symmetry acts non-linear. I know. I was so nervous to say boson for discrete symmetry.
No. It's the point. Of this.
I'm glad you feel comfortable about it.
I feel that your vacuum state is invariant and this is free, right? And that's it. Because then you have phenomenalization.
But it's not created by a current. There's no current. Right?
It doesn't matter.
Well, in Goson's paper, that's how he constructed the Goson boson.
No, but forget about current. What is important that you have vacuum which is not invariant.
But that's not how Goson said it. Right? Goson, okay, you can call it the boson, but I feel nervous to attach the adjective.
No, but I'm trying to say that it is a way to preserve the notion of
that's fair. That's
fair. No, you see, because in this sense, even
that's fair.
I have one question. So you I did when you quantize the zero mode, of course there's continuum instead of the general state. Yes. But now we are and we don't have thermodynamics, right? It's just too much states.
But they're infinitely heavy.
But now you're talking about the mode with KX.
The zero modes quantum mechanically are infinitely
heavy. But the KX, KY mode, you can take one.
Yeah.
say that.
This is.
Just gave me this.
Oh, I see.
Yeah, okay, I was not mentioning it's not maybe not very.
Oh.
Also, we improve that. And I think I agree with the fact of opinion in a certain way. So these generalized anomalies, maybe we can talk at some point, but I have a construct this generalized anomaly. You don't have it on our phone. Okay. But in general, what people do, they compactify an phone. So this is a generalized anomaly. Not my fault. Here, I have this generalized anomaly. Completely. Sorry? They're both torus. It's not localized. Okay, so it is up to him. But I already have this duty to deliver, right? So would you refuse to cover something about the infinite volume? I'm sorry, but no, but the generalized anomaly is a technical question. Never there. I'm going to be in the hotel.
What time?
So, attention is 6:30. Generalized anomaly. There, I mean 6:30.
Yeah. So if you try to put it
because it works for me both ways. I have a car here. So, sorry?
You need to impose. I mean, if you have fermions, you need to impose.
Yeah, exactly. Something like that. Yeah. So okay. Anyway, don't leave me uninformed. So it's my responsibility. No, we can do it different ways, right? But yeah. So depending when it.
I didn't get the invitation, so I didn't.
Okay, so this complaint is not to me. Okay, my diagonals, a center group and a subgroup of the more people to deliver, and also not a fractional instantons that contains both flavor and. Let's do it. Both things.
Usually arises because the GQ
when we are talking. It's the diagonal part in the center of the gauge group and the subgroup of the flavor group. It's not just the center of the gauge group. The center of the gauge group acts directly on the fermions. So you cannot, so it's not a center symmetry. Okay. So you have a certain Zn that is part of the gauge group. And then you have a Vn that is part of the flavor group. Yeah, it's part of the one variance. Okay, so there is these two symmetries are the same. So you take one and the inverse, they don't act on the third. So it's effectively a new center symmetry. So a Zn symmetry that does not act on the third. It is composed a little bit by the gauge and a little bit by the flavor. With this, you can create a new center symmetry. So it's this thing that you gauge when you say you construct a.
No, but that's
this is effectively something that does not act on that. So you can do this fractional.
But that's what puts that.
For this one, it doesn't care about the boundary. What kind of?
Yeah, so here
you can do it also with the fundamental, yes. Because
okay, so if we compare it for any directions,
yeah,
then in SUN overlap in the SUN and one.
Yeah.
So for SUN, they already imposed the boundary condition, but how? So you need to like kind of use also impose the boundary condition on U1 stuff and to kind of unwind it.
Exactly.
Yeah.
So is that
so they should care about it. So they should care about the boundary condition, right? Because you already impose it in somewhere. And,
It's an example where you have
There's the current, but there's the
So
part.
this you can do it for QCD, for example. You have done exactly stunning. You take QCD with fundamental fermions.
It's the
You
matter
have
of.
the n center of the gauge group that
So
acts
here,
on the fermion.
put it in
Then there is
context.
the n subgroup of the U1 baryon. And you take the diagonal part that does not act. And you construct fractional instances with that thing. You construct generalized anomaly with that thing.
It should be done.
Yeah, so this you can do for just in the fundamentals. You combine.
Yeah, I mean, you could also combine the SU and U1. The U1.
Yeah.
In the continuum limit.
Okay, so you can.
So we agree on that thing.
Yeah. I agree.
So the first step is normal generalized anomaly, like when fermions are not charged onto the center of the gauge, like QCD with the charge. Then you have normal generalized. Then you can have a little bit more complex version when we have like QCD in the center, and you combine it with the end that is part of the U1 baryon, and then you create some.
So this coefficient.
Yeah, but then don't
And then there is what we are doing. That here is the problem. We are doing it in a theory where you combine the end of the gauge with something that is not really the n inside the U1. The U1 times Z2 is a Zn contains in a U1 times Z2. So the Z2 part is discrete. So it's a Zn inside the flavor, but it's not entirely inside the U1, it's inside the U1 times Z2. And this creates the problem. You cannot do the fractional 1 over n. So instanton
Then the question is whether the thermodynamic.
on the torus, for torus, because you cannot solve the cross-cycle condition. And the problem arises because there is this.
Both are equally good. Theoretically, yes. If you work in a lab, I don't think.
Originally, you have two U1s. U1
This one is.
and U1 of the eta. But then there is the ABJ anomaly, and it breaks into U1 times D2.
No, but when you say.
It is inside U1 times U1. But then there is ABJ anomaly breaks into U1 times D2. And our Zn is inside this U1 times D2.
No, but you can choose another parameter. Eighth dimension, what do you mean? Yeah. That's another dimension.
For you tomorrow in the conference. Come here. This is the example. I think this picture is very well. So this square here is U1 times U1.
Right, but
This is U1 psi. This is U1 eta. Classically, your symmetry is U1 times U1. Mechanically, you have the anomaly. The anomaly brings. This is the case for gauge manifolds. The anomaly breaks, for example, U1 psi to Zn plus 2.
That could be better, but this is the
Z5.
Yeah.
So only this skip points.
Preserving this.
And U1 eta is broken to Zn plus 2.
It looks like this is like turbulence, right? You can start with
Really, they're all connected by a single U1, non-anomalous U1. It winds around the top.
Right, yeah.
And this non-anomalous U1 covers all the discrete points. Okay. For n odd, So the single U1 that starts from the identity does not cover, you need two copies. And even the U1 times U1 is broken to U1 times T. This is the red one that winds and creates a certain U1. But then there is a disconnected one. The odd one can never reach by the red.
Ah, you said the red one is not in the same copy of the blue one.
Yeah, exactly. So you think of your torus, you have your U1 winds around, and so the even numbers of Zn plus 2 and Zn plus 4. The odd numbers are taken by another.
Okay, so how do you write down the transformation of this? I mean,
No, okay, you can write it down. It's not difficult. And then the Zn that you gauge is intersection between the gauge group and the Zn included in this. So you need to pick both U1 and Z.
so then you have a
Then when you have anomaly when you put some torus. But then there is this problem that the fundamental fractional instanton, the one that has charge 1 over n, you cannot do it because of this treaty. You need the defect. Because you cannot solve the cycle condition.
because they introduced some kind of the flux.
Yeah. What you can do is to put a pancho. It is essentially a Z2 flux. And this is a defect. So now the whole idea of taking this generalized anomaly and consider it as something that can be used in the infinite volume limits becomes questionable. Defect. If, for example, if you find out that the anomaly is localized on a defect, then this effect does not supply. This is something that we have not done. So I think this could be the point that maybe is our mistake, and that Tom is right. I don't know exactly what, but I think this is my point of view now. But we haven't really done it, so I don't know.
Why might the defect does not survive if you put it in the
But the point is that when you do this fractional instant, the fractional instant is homogeneous. The topological charge is spread homogeneous all over the torus. So this generalized anomaly is because you have fermion zero modes. The fermion zero modes are also homogeneously distributed among the torus. So suppose that these fermion zero modes are localized on a defect. If taking the infinite volume limit, they remain localized on a defect. So they are not there in the infinite volume limit.
Yeah, so there is no.
And so maybe you cannot use our argument in the infinite volume limit because it's really it's applicable only with these defects. Okay, this is just a pure conjecture. I mean, I'm just trying to. Our work and Tom's work, they don't agree.
Yes, yes.
But they're written on different perspective. Okay.
They say in R4, but you say that's in T4 with some defect.
Yeah. So, mistake, where is the disagreement, or where is the issue? I don't know. So that could be an interesting problem, but. So, okay, Tom's perspective is that we are completely wrong, but.
I think probably this just arises from what you were arguing about the quantization conditions, about the gauge field in two things, right?
Yeah.
So
what is your opinion? What do you think of this? I mean, the technical part of Tong's paper is correct. I don't agree. I don't disagree with that. I mean, the can put this flux on a torus, and they prove it also more generally, but on any.
I think I just don't realize before that you put it on like some complex stuff, then you argue with this.
But you always have to put the compact sets to the generalized anomaly. That's always the case. And always generalized anomalies arise on manifolds. I mean, even a simple one, no? Yeah. Like the one on let's give it a joint fermions. Okay, what's like generalized anomaly or not? You can fractionalize it. So you assume that
this is something.
It's compact, but then you take the volume limit. Okay, if this is constraining theory on the compact manifold for any volume, and everything is homogeneous. But there is a little passage that maybe we take. So I don't know what is your point of view on that.
What I confuse is from the very beginning that what's the correct gauge? I mean, the correct global symmetry group we need to consider. So I think once we identify what's the correct gauge group, the global symmetry group, we know then the following will be much easier. That I mean, try to find what's the right global symmetry group.
This is one point. Then there are also other points, but yeah, I think in our first papers we kind of maybe we were a little bit too fast. The sentence here because we didn't start this. That was our mistake, I think. But still, in any case, no matter who is right and who is wrong, I don't understand how to combine the two things. Where is the issue? Where is the mistake?
Yeah. I don't even know how do you interpolate between these two conditions, because as you say, if you have some open space, then
the rough is something wrong for what we're saying.
Okay, yeah, go ahead.
So you are the exponent of something. Here you are the standard thing.
Yeah.
Minus 88.
Yeah.
Okay?
Yeah.
But the problem is that this is not there. You know, and that's seen.
Yeah.
And so just is not here.
The status of the problem.
Yeah.
Define.
Yeah.
So,
I mean,
no way.
Totally define. Don't say that. So, everything you're doing is wrong.
What's the coefficient in front of the well, it matters.
Well, but now it's
Right, because you put on different spaces.
Exactly.
But it matters what gauge transformation you decide to apply.
Okay. So
That
A goes
doesn't
to
matter.
A. plus
We don't know. We don't know.
and then phi goes to phi minus lambda.
What's the heuristic of phi? It's phi compact. But then that's a trivially gapless. That's not EDA because vanishing curve.
It's a different theory, but it's getting one.
Well, there are also many other issues. Yeah. Well, let me say a little bit more. So, I mean, you can consider this case Lagrange.
Yes.
This is the same as ADB and over 2π. But that's very different from ADA. Both of them have Harrison part still. I don't think you can do this for ADA.
This is equivalent to
Yes, yes. And put duality transformation.
I thought that's
So you first approximate this like this. For F is a Laurence multiplier, then the low energy is 57. And then you will integrate out the and that will make the 0, and therefore locally is. Then the left over is this, the end is the coefficient is a little bit more out. But it's common that the Higgs Lagrange is ADA. That's a CN case. An ADA is very the invariant distinction is very yeah, it's a different theory. It's a different theory. Yeah. Actually, with this it's like yeah, that's one of the but it's not literally. It's not
In my mind, it could be a monoid, could be a ring. You told me that.
Yeah. There's something like a stack that was the ring.
Oh no, it's a ring. Yeah.
Maybe it's the number of
that works.
Well, Larry, I thought initially it's you when you were younger.
That would be much harder to find that picture.
Story problem. Put boundary conditions on the rectangle. One side of the right side of the other side of the right side of the direction. And the germs of the courts working.
So you just take that. Okay.
Okay, take it away. Well, it's a pleasure to be here after a bit of a gap. I don't remember the first time I came here to Minnesota and gave a talk to the two Mishas in Arkady. It was my first introduction to Russian style seminars where the questions just keep coming for an indeterminate length of time, but they're good questions. So we've had a number of talks, and we'll hear more, that are beautiful examinations of symmetry, subtle consequences, and that's lovely stuff. But I just want to emphasize my talk is going to be different. My talk is much more in the spirit of famous comments from Richard Feynman, which I actually heard long ago, which was pretty much shut up and calculate. So this is a talk about ongoing work, which was said to be appropriate for this meeting. So this is work with postdoc Sebastian Weber, who I've had a lot of fun working with. And the topic is computing holographic collisions. This is an application of holography or gauge string duality. I'm assuming everybody understands roughly what that is. If we need more of a refresher, anybody please ask. But of course, the great promise of holography is that in principle, it works for any state. It's not about vacuum states. It's not about equilibrium states. You can apply it to far from equilibrium states with non-trivial dynamics, as long as you can roll up your sleeves and really calculate what happens in the dual description. So I want to talk about applications that are motivated by heavy ion collisions. I'll say a little bit about that. It's just a recap. I'll then recap some old results, that some of which are a decade old now or even more, some a little newer, but stuff that was done previously. And then I want to talk about recent work, which, to be honest, is a very, very simple approach. It just takes sitting down and rolling up your sleeves to study how well it really works. And Sebastian and I are in the middle of that. So we have some new results, but some things are grayed out because they're still in progress.
What collides with what in this point 3?
So
I understand heavy ion collisions. This I understand. But what in point 3?
So if you will, it'll sort of be most, if you'll just take a nap while I recap real heavy ion collisions for a moment, and then I'll really answer your question. Okay, real heavy ion collisions, right? What really happens, right? Take two big nuclei, slam them together at ultra relativistic energies. They are enormously Lorentz contracted. So it really is like two little thin pancakes hitting each other. They go splat and stuff happens. Now, how should you think about that process? Well, starting at energies where energy per nucleon is much, much larger than the CAQCD strong scale, you can describe what happens as liberating some huge number of partons, quarks and gluons, mostly gluons, and it forms stuff. Now, I don't want to get too hung up on semantics. I'm going to say you form a plasma, right? It's a whole bunch of charged particles, non-abelian charged particles running around. It is far from equilibrium. And for reasons I'll briefly touch on, I will argue, we know that it is strongly coupled. So certainly the notion that collisions like this were going to produce something which was well described by weak coupling descriptions of quarks and gluons, and that you should just instantly think about asymptotic freedom. I mean, that was naive 30 years ago, and sensible people understood it. Everybody else had their nose rubbed in it when the first results from Rick really came out. So there's lots of reasons to say you're producing a far from equilibrium, strongly coupled plasma, and what happens? It expands, it cools. At some point, it becomes appropriate to really just describe this as a fluid. It's a system whose hydrodynamic modes are exactly the same as any other neutral fluid described by simple hydrodynamics. And this one signature of being strongly coupled is it's a relatively low viscosity fluid. Now, in terms of being able to calculate once somebody tells you that hydrodynamics is a good description, that gives you a pretty simple effective theory. You can, put hydrodynamic equations on a computer, you can integrate them, although even that is not trivial. There's lots of discussions about you have to do a little better than first order viscous hydro, but still that's relatively well understood and doable. In reality, what happens? That fluid expands, it cools, eventually in QCD, you reach the point where hadrons form. Quarks and gluons bind back in together into hadrons, they continue flying out, there are final state interactions, eventually they reach the detector and get measured. What I want to focus on is basically the gap, is this initial phase before you can just say hydrodynamics is a good description. Now, in a lot of modeling of heavy ion collisions, because there's not great theoretical control of that first phase, people just ignore it. They take some model of what the energy density is just at the moment that these nuclei collide, and they try and pretend that that's initial data to run hydrodynamics. That's clearly not a great approximation. That was a move of desperation. And so the theoretical challenge is just do better here. And that's where holography will play a role. Okay, I won't say too much about this except to say you measure lots of things of what comes out in heavy ion collisions. One is the angular distribution of particles that come out. You can look at different, expand it in a Fourier series, calculate different coefficients. The study of both what's called radial and elliptic flow is one of the lines of argument that underlies saying you really need to think about this as a low viscosity, or in other words, strongly coupled fluid. There are numerous other lines of arguments, including the behavior of screening masses in thermal equilibrium, that again tell you that the plasma at the accessible effective temperatures that are being probed, this is not in some weak coupling regime. This is a strongly coupled plasma.
So what temperature do you mean? What temperatures?
That was what was that? That was a spontaneous rejection of the talk? What?
Yeah, I mean that you said something which is not true. Okay, so at what temperature do you mean this regime, what you call strongly coupled plasma? What temperatures? Without temperatures or scales, it tells me nothing. It's out of equilibrium, right?
So temperatures that are well above.
Very high, yeah? Very high temperature.
Well, that are well above the temperature at which hadronization happens.
Okay, hadronization, we know it happens at chiral restoration temperature.
Anywhere from a couple hundred MeV to 500-600 MeV.
But then this
we
is
can discuss this later.
Okay.
Believe me, strongly coupled.
Okay, I believe it.
But when you're saying elliptic flow, I would say that okay, it's a way to say that it's not plasma, right? In a sense, right? No, I mean, because if we were talking, understand that plasma in a kind of original sense of kind of weakly interacting particle.
Whoa. So this is where I don't want to get hung up on the words. If that's what you mean by a plasma,
yeah,
then fine. It's not a plasma.
Yeah, okay.
It's goop. It's strongly interacting goop.
Okay.
No, but this is still a system of other-like objects. It's not pretty obvious. Other-like objects.
There's no identifiable objects. It's goop. Yeah. It's dense. It's stuff.
Yeah.
All right. But in addition to elliptic flow, there's been a lot of studies of higher moments. There's a pretty simple argument that says the measured third moment is really telling you that if you think of this collision as like literally the beautiful pancake that somebody has for breakfast, that's pretty uniform and quasi-circular, that's not a good model. That in order to get a large V3 of the size that's measured, basically the energy density of the stuff that's being collided has lumps in it, which you can think of as, you know, some snapshot of the actual distribution of the nucleons that made up some nucleus, if you will, but just think of it as being lumpy. There's a lot of evidence that
Blueberry pancakes.
yeah, exactly, exactly. So that's a hand-waving description about some of what we know about real heavy ion collisions and real QCD. And now the reality is calculating that is too hard. We have no controlled, fully controlled theoretical approximations that are capable of just jumping in and calculating. So we cheat.
When you speak of hot QCD, okay, hot QCD is separately n equal 4 is not hot, right? It's 0 temperature.
So here by hot, I mean hot enough in QCD to be above the crossover, which is not really a deconfinement transition, but it's a well-defined crossover where the entropy density jumps dramatically, grows dramatically. Here, I mean n equals 4 at any non-zero temperature.
No, but then if you put temperature, you ruin supersymmetry, right?
Doesn't matter. It's the n equals 4 theory considered at non-zero temperature.
Okay, okay.
So qualitatively, just to say, what are the similarities? What are the differences? The important point is, well, I just argued that the quark gluon plasma you create, I'm going to call the plasma, don't think of it as weakly coupled, but obviously it's not abelian.
No, right? But on n equal 4 side, you can call it plasma for weak interaction, right?
Well, I'm going to call it plasma even when it's strong interaction. In both cases, right? I mean, even if they're interacting strongly, the constituents are gluons, non-abelian gauge field fluctuations, and charged matter. It's just in one case, they're fundamental representation fermions, in the other case, they're adjoint representation fermions and scalars, but still, it's just a bunch of charged particles running around under the influence of a gauge field.
For supersymmetric symmetry, your lang is certainly correct because there is no confinement, there are no hadrons, nothing.
Yeah.
But identifying supersymmetric theory with hot QCD is for me questionable.
Well, so this is not, I mean, they're clearly different theories. Yes. This would be a terrible thing to do if we were interested in physics where hadronization is a big part of the story. If we were interested in talking about the actual particles that come out, that would be nuts. The argument is in real heavy ion collisions, there's that early stage well before hadronization, before I can just view it as a simple fluid. And that's what I'm really interested in.
But in say n equal 4, if you will take this arbitrary coupling to be small, it would be no fluid, right? The fluid would be only when coupling larger than something, or how? No,
at any non-zero temperature, it's still
fluid.
Okay, you know, the hydrodynamic modes are the same. Real QCD, I will argue in terms of a wide variety of thermal properties from lattice studies. There's good evidence that the dependence on the number of colors is actually quite weak. Equally true for a lot of quantities in n equals 4. The regime of QCD I'm interested in, I've just emphasized it's strongly coupled. N equals 4, that coupling is whatever you want. So I'm going to crank it up and make it strong. QCD, of course, is non-conformal. There are real mass scales in it. But in this regime that I'm interested in, all the other mass scales other than the energy density, or if you will, an effective temperature, which is just defined by it, are not all that important.
But
I
that
will
should be
argue this
above
is-
500 MeV. Then your regime should be above 500 MeV.
No, no.
Okay, this is
We
showing
have to
results.
talk about that separately.
Okay.
So, I mean, it's not perfect, but it's quasi-conformal. You can see that if you look at a variety of calculations from lattice gauge theory. Of course, n equals 4 is exactly conformal. And again, the argument is not that this is perfect. The argument is that this is close enough to be interesting to study. Okay, so I think that's clear. The goal is to use this wrong theory to study QCD, because in the wrong theory, we have better calculational techniques. Okay. What are we now studying? Misha's question.
Yes.
So real heavy ion collisions, you have a real heavy nucleus accelerated, well, technically not to the speed of light, but to less than the speed of light by only 1 part in 1,000. In n equals 4, because it's conformal, we know that there exist states which look, well, states whose energy density looks just like the energy density of that Lorentz contracted nucleus, or anything else you want. Craft the blob whose energy density has whatever form you want, and just make it move at the speed of light.
Excuse me, isn't that true? If you take a conformal theory, which n equals 4 is, but then you heat it, isn't it true that in a sense you lose conformality and the coupling constant in a sense starts running and the theory becomes non-conformal?
Well, I still wouldn't say the coupling constant runs, but let me be clear. So what I just said is preparing an excited state in n equals 4, which is some lump of energy density moving in what is otherwise a vacuum. This is not moving in the presence of some thermal bath. It's just literally, you know, something moving.
Okay, at 0 temperature, of course, you can prepare a wave package.
Okay, but if you can do that, you can do 2. And if you and in moving in opposite directions, and then you can run them into each other. And that's now going to produce a state which, well, stuff happens, right? Energy is, of course, conserved. You're going to have a flux of energy out in various directions. You'll produce some lump, which will expand and cool, just like a real heavy ion collision. And that's exactly what we're talking about here.
So, so the logic here is that you related to n equal to 4 because you see that because that is the prototype of holography. But we can do holography also for non-conformal backgrounds. So you can bypass this going to n equal to 4 and try directly to cook up a holography.
No, but
Yes, in principle, yes.
So what is the technical problem?
Well, so to use holography in n equals 4, which is the simplest example, to actually turn my words into results, what do you have to do? Well, you have to, I mean, what I just described was a scattering experiment. So my argument is I can do this scattering experiment in n equals 4. I can do it using the holographic dual description, but it's still an honest to God scattering experiment where you've got to talk about initial data, you've got to do the evolution, you've got to see what comes out. And in n equals 4, we have the simplest dual description, which is just
a difference between Newton's model where the metric is somewhat different than
this is not a metric you can write down. So this is saying, so in n equals 4, the dual description is regular Einstein general relativity in 5-dimensional asymptotically anti-de Sitter space. So you've got to actually just sit down and do a gravitational initial value problem in 5 dimensions. You've got to solve 5-dimensional partial differential equations with the right initial data, the right boundary conditions, and roll up your sleeves and see if you can do it. Now, if you can do that, in principle, you are invited to now do it in a more complicated holographic model with additional fields, additional dynamics. But solving 5-dimensional GR in time-dependent, non-trivial states is not easy.
Okay, let's assume for a second that you solved it.
I'm going to show you.
For a second.
Yeah.
What does it tell you about heavy ion collisions? I don't think it will tell you anything about the heavy ion collisions.
Well, I will disagree with that, but I will qualify it, right? The argument will tell you some things. So in the real heavy ion collision, that pre-hydrodynamic phase, what's happening? Somehow you're going from the initial moments of the collision to, well, to when you can first change description to an easier way of calculating, which amounts to hydrodynamics. So what I'm inviting you to think about is the challenge of how do I connect the initial collision and your understanding of the initial collision to initial data for hydrodynamics at on some later hypersurface. Well, what do you need? For do that, you need to know the energy density and the momentum density. That's the initial data for running hydro.
But then you are saying that in certain way you believe that once you have this n=4 plasma or whatever at non-zero temperature, then you are saying in terms of what you said, energy distribution or whatever, then it doesn't matter whether it was made out original fundamental QCD stuff or from n=4 stuff, right? Because then you are not interested even in this composition, right? In certain sense.
Well, I'm arguing that the dynamics in this regime for this class of initial states is very similar in these theories.
Yeah. But then you are saying that it's kind of more universal, right? Because in this way, then it doesn't matter what was original theory if you go into this vision.
For matching comparable initial states, yes.
I see.
Okay, so remember, the alternative is pretending that this pre-hydrodynamic evolution doesn't exist at all, which is completely wrong. So, I mean, just make sure your bar for progress is set appropriately low. Okay, old results. Solving 5D GR is not easy. So if you think about, this model of a heavy ion collision as a thin pancake, an obvious simplification is to say, can I just pretend that that pancake is really infinite? That is, can I literally ignore the two spatial directions transverse to the collision axis? It's a natural place to start. There's been a lot of talk about this in various forms of heavy ion modeling, and it's a natural thing to do here. So it's something that I got interested in with my then student, Paul Chesler, over a decade ago. And even this is non-trivial. Even this is doing 3-dimensional partial differential equations. There's lots of issues of numerical stability and how you discretize. I could give you a whole nother hour-long seminar about computational details, but the bottom line is you can do it. And more recently, lots of other groups have also done it. And here are just a few pictures. So what you're seeing here is just a picture of energy density, which is extracted from the near boundary behavior of the metric as a function of time and the longitudinal direction of the collision. So on the backside, you're seeing 2 projectiles come in, and you get to craft the longitudinal, the profile of that energy density. So you can have very thin shocks, you can have a very thick shocks. Computationally, the thinner you make something, the greater dynamic range you have in a calculation. it's harder to calculate. So relatively wide shocks were done first. And so what do you see? You see stuff coming out after the collision. This is stuff essentially approximately going out on the outgoing light cone, but with energy distributed in the region in between. This is exactly what happens in real heavy ion collisions, right? So you can study that in more detail. I just have some pictures up here saying you can successfully do much narrower shocks. You can do shocks that are asymmetric, and it works. And even out of this, you can ask questions like, what is the regime in which hydrodynamics is a good approximation? What is the regime in which it's not? How long does it take for hydrodynamics to first become a good approximation? You know, how rapidly does the energy that's close to the light cone decay? So a variety of interesting questions. But I don't want to spend too much time on that. That's the warm-up.
If these are light shocks, could
Yes.
you linearize your equation and solve them exactly? And does this simplify the problem?
For one shock, which just moves, yes, because it's just completely stationary.
Yes.
There's no dispersion.
I see.
That you can absolutely do.
But two, no.
Two, absolutely not.
You can use a DBI that describes exactly the scattering of two shock waves.
Well, I mean, so one has choices. So my choice was to change the problem from QCD to n equals 4 super Yang mills, and then do a strictly controlled, honest calculation of n equals 4 using the dual gravitational description. No further approximation.
10 minutes, yeah.
Okay. Okay, that's the warm-up. A lot harder is to really do localized collisions, something that really does resemble that pancake of a Lorentz contracted heavy nucleus. Paul and I succeeded in doing this, 7-ish years ago. And, I showed you the little movie there. Again, if you just imagine what does the actual energy density in a real heavy ion collision look like, it's pretty much what you see there. And you can, of course, take snapshots. This is the energy density at different moments of the collision, pre-collision, instant of collision, as post-collision stuff starts separating. Once again, you see deposited energy in between. You can study it. You can extract radial flow. You can actually see that there is significant flow before hydrodynamics becomes a good approximation. So that's a key part of this mapping from the moment of collision to hydro. Lower plots are showing energy flux. This is actually showing the residual for testing when is a hydrodynamic approximation to the stress tensor good. So basically, we're sort of the blue-green little blobs here you see developing as the time goes on. That's the region that you can really describe as a fluid that's behaving like a fluid. Okay, so old stuff. I will argue that it taught the community some interesting things, legitimate questions. Didn't answer everything by any means. You can get much more quantitative. There's a near universal form of rapidity dependence of what comes out. The actual pattern of flow is close to being boost invariant. You can understand asymmetric collisions in a remarkably simple way. This is what really has a lot of consequences for proper modeling. You see that there's quite rapid onset of when you can use hydro. And one of the big things you learn is that the hydrodynamic description actually starts working sooner than you had any right to expect. I mean, textbooks would say hydrodynamics is a long wavelength, low frequency approximation. You need a large ratio of scales between how things vary in space and what are microscopic length scales. In reality, that ratio needs to be
And when you see that, that's just from comparing the results that come out of your calculations
Yes.
to this hydrous.
Yes.
It's not, yeah.
No, that was not obvious in advance. That's just saying, when does the first order viscous approximation to the stress tensor actually well approximate the actual stress tensor that was calculated with full GR? Yeah.
So when you get to this hydro phase, it's a black brain.
Yes.
The black brain cannot decay in ADS, right?
Well, so technical details. So space, I mean, ordinary three-dimensional space computationally is not infinite. It can't be. So really, you've got periodic boundary conditions. So really, you're running, you know, simultaneous collisions in periodic boxes, which means there's actually a black brain from the outset. It's always there. It's just a question of what energy scale is it at. Okay. Limitations. There are definitely limitations. This was barely feasible for us 7 years ago. And, you know, it's tough numerical stuff. So you're constrained by either time or memory, or in this case, both. The good news is if you use good approximations for approximating derivatives with suitable finite differences, you can get by with a relatively coarse grid. Using a good approximation means using what are called spectral methods, which really means using a relatively non-local definition of a derivative. But even so, just storing the data you need to deal with to calculate one time step sucks up a lot of memory. Technically, in order to deal with that black brain and where the horizon is, there's a condition you have to solve to fix it. That requires solving an elliptic PDE on the horizon that you should think of, you know, it's like solving a Poisson-like equation. It's linear. What's the big deal? But the big deal is it's dealing with a matrix whose dimensionality is about 250,000 in this fairly coarse grid. Of course, you parallelize as best you can, and this took months. And the reason I'm talking about it now is, well, this used the simplest conceivable model of that initial projectile that just had a Gaussian energy distribution. Instead of having an aspect ratio of hundreds to thousands, which is the case of real Lorentz contracted nuclei, we had an aspect ratio that was like 4 or 8. It was the best we could do. We didn't have the lumps that are actually relevant, but it was the best we could do. How much time?
5 minutes.
Okay. So more recently with Sebastian, we got to saying, are there things we can do that will just speed up the computational burden? And the one pretty obvious, nothing subtle about it at all, suggestion is to actually turn the large aspect ratio of what we'd like to be able to calculate. Can we turn it from a problem into a benefit? I mean, the amount, what it amounts to saying is, if you think about the scale over how rapidly our geometry is changing, it's dramatically different in a longitudinal direction than it is in transverse directions. So can we just take advantage of that by treating transverse gradients as small compared to longitudinal gradients? Short answer is, yeah, you can. You can, I can talk about sort of formally how you do it. You literally are going into your Einstein's equations and looking at terms which have 0 transverse derivatives or 1 or 2 and systematically expanding things. In interest of time, I won't really dwell on that. You're doing an expansion. So obviously you get some sort of hierarchy. You do the 0th order first, that really amounts to solving planar shocks. And then you do 1st order corrections. And then in principle, you do higher order corrections. And at every order, you get something which is now linearized in the correction to the previous order. So you're basically solving what's called the Lichnerowitz operator on your previous order solution to improve it. But you got to actually do it to see how well it works, right? You have to go to high orders to get decent approximations or not. So obviously, now I am introducing an approximation. There's going to be truncation error. The advantages are it really does speed things up and it takes a lot less memory. It enormously simplifies that horizon fixing equation. And punchline, it works a lot better than we really had any right to expect. Now, just eyeballing it, this is old results solving full 5D-GR, no approximations. These are results calculated with just 1st order in this transverse derivative approximation, but using the same initial data that were here. They didn't get plotted exactly the same way, but you're supposed to look at that and say, yeah, looks pretty similar. At least it's not terrible. You can, of course, be more quantitative. Here are comparisons of stress or components of the pressure as a function of time, or radial flow, again, at different instances in proper time as a function of where you are on the transverse plane, energy density at one instant in time as a function of that didn't get labeled correctly. Energy density at 2 different places. But what are you supposed to look at? The red dots or the red curves are the full results. The blue or the kind of brownish curves are our 1st order approximation. And of course, they differ. They differ more at later times. They differ less at earlier times. The bottom line is up at times where you have reached the onset of hydrodynamics, basically your errors are 10%. And earlier, much less than that. So I think that's a success with a substantial speed up, with less memory requirements. It's going to let us do more interesting initial conditions. This is something we have running right now that literally is now a lumpy or granular initial data. It's very similar to what people are using to do fancy but less justified modeling. And that's in progress. Something I think would be interesting to do is to now say, in addition to strong interactions, there is, of course, electromagnetism. There's been a lot of discussion in the heavy ion community about the importance of that and so-called chiral magnetic effects and stuff. Almost all those discussions are using ridiculously oversimplified estimates of what the actual electromagnetic fields are doing. Nobody's done a calculation where you just do it correctly. And I think for the first time, we have a fighting chance of doing that. With that, I thank you.
Okay, thank you.
I wonder when you said it about emulation, my impression is, it might be wrong, that your implying that emulation was at the very beginning, right? So you started from emulation. So it's not explanation of emulation. It's just that once you started, how it develops.
Yes, there's a lot of argument that's, I mean, it's the logic is sort of reversed, right? I mean, there are measurements of these different correlators of what comes out. And the claim is, in order to reproduce what's seen, it must be the case that there is some sort of granular structure. And so now there's just, there's pictures that says, okay, we've got all these nucleons running around, we're taking a snapshot, they're not going to be perfectly uniformly distributed.
Right, but it could be that, for example, cumulation would appear in the process of your calculation, like some kind of instability, for example, right? You started from uniform and then you get some, you know, kind of developing of something. And you are saying that it's not the case, right? That's what you are saying. I see.
Yeah.
Some further question?
Is there any way to address also the issue of hydrogenization in this kind of
so this is where the question of what holographic description is being used becomes key. So
what's done about that? Right?
Well, Paul and I have spent a lot of time talking about this. It's not easy. So yeah, you'd love to say, can we now just use a more elaborate holographic model, which is not conformal, that mimics some of the physics? It changes a lot of things. So I mentioned to Zohar in these calculations, it's not like a horizon forms. There really is a horizon at all times. In non-conformal models, it's a different story. It's a lot more, and we just haven't figured out how to make it work.
It was addressed at the time by also only Toby Weissman and Shiraz Minwala, the numerical calculation of plasma ball inside the confinement.
In a very symmetric situation.
Yeah,
Exactly.
nothing much was done there.
And of course, one of the interesting things there is this is where taking the large N limit in those models is actually really changing things. So in these models where you really have a first order transition that you could call a hadronization transition, because you're at large N, the system gets hung up there for a long time, not like the real world at all, right? I mean, a parametrically long time.
But also large N affects, you know, whether you have string breaking or not. And you would naively think string breaking is super important for actual hadronization in the real world. So large N could really change things.
You see, I actually made a comment to you, Tom. Concerning categorization, you need some kind of confining physics. In order to have some kind of confining physics, you must have proper symmetry of electric field, which is now mathematical fact. In this kind of approach, I have nothing against, but it doesn't have.
Yeah, no, this has no.
Yeah, this is
no
basic. So then you cannot address the question of categorization. It's illegal question within this approach.
Right.
As approach itself, it's okay.
Yeah, but in terms of actually grappling with data, right? What I talked about was this early stage where there's real theoretical puzzles. When you can describe things by hydrodynamics, I mean, even really calculating 3 space dimension viscous hydrodynamics is non-trivial, but it's easier than what I've talked about here. And then to describe hydrodynamics, you have data-driven, what amounts to kinetic theory, right? Cascades, into data.
Okay, so let us thank Larry for three. Yeah, but yeah, please.
This microphone.
I should indeed.
you hear me? Okay. All right. Thanks for inviting me to give a talk at this workshop. I was initially worried. I was thinking of hiding because my talk has no QCD in it, even though the title of the workshop says Continuous Advances in QCD. But I'm hoping to make some connection with chiral gauge theories at the end of my talk, but it's going to be a very brief mention. So I'm going to apologize at the beginning and then go from there. So the talk I'm giving today is based on 2 papers that I wrote recently with David Kaplan at University of Washington. The last one listed here appeared yesterday, if you're interested. All right, so what is this talk about? Let me unpack the title a bit for you. So this talk is about fermion edge states in gapped free fermion theories. Mostly I'll talk about just relativistic quantum field theories. But as you know, they describe the physics of topological materials very well. And so what I'm talking about is relevant for topological materials. What I'm going to talk about here is, a way of unifying these different types of free fermion edge states using a picture that resembles the Hall effect. I'll demonstrate using a simple example. And I'll probably not have time to discuss the last point, which is there's a role of the topology of the Dirac operator, which plays in quantization of these corresponding Hall currents, which I'm going to call generalized Hall currents. So with that, let me show you here a bunch of pictures. I'm not drawing the time dimension. These are pictures of topological insulators. This one is very familiar. This is the 2+1 dimensional bulk quantum Hall system. And you have chiral edge states on the boundaries. This is, of course, described very well by a relativistic quantum field theory of a massive Dirac fermion with a domain wall at the edges. This is a picture of a 3+1 dimensional topological insulator with 2+1 dimensional edge states. Again, you can describe this using a Dirac fermion with a domain wall in its mass. That's a 2+1 dimensional domain wall defect. This is a vortex string in 3+1 dimension with a 1+1 dimensional edge state. Again, you have chiral edge states there. And this is a 2+1D bulk with a 0+1D defect and so on. So here in this talk, I'm just going to claim that this one is a little bit special from my perspective. And the reason is because we have chiral edge states. I am defining it to be special in this case. So let me quickly recap why I think this is a special example. And to explain that, here I'm drawing the edge of a quantum Hall sample. So as you know, if I'm looking at the boundary of a quantum Hall sample, if I want to draw the spectrum there, I have either a right moving or a left moving massless fermion living on the boundary. And here I'm just drawing the right moving one. And as you know, if I apply an electric field, the population of the right moving branch will go up. And there's no left moving branch. So vector current itself is not conserved. So this theory by itself is sick on the boundary. But as Fiona discussed in her talk, when this boundary is placed on, when it's actually a boundary of a quantum Hall sample, there's current flowing from the bulk to the wall, which helps conserve current. And so then this theory becomes consistent. So that's what I call special. Now it turns out, of course, this picture does not hold for other kinds of systems, some other kinds of systems. For example, you could have, odd space-time dimensional defect, where there is no notion of chirality on the boundary. So, it doesn't make sense to talk about current flowing from the boundary, from the bulk to the boundary. So this is one example, 3+1 dimensional topological insulator with 2+1 dimensional edge states. The picture doesn't hold. Similarly, you can have 0+1D defect states in 1+1D topological insulators. Again, it's an odd space-time dimensional defect. So there's no current inflow picture. And then you can have theories without any continuous symmetries, which can happen if you break the fermion number symmetry, for example, by some pairing. And then you can end up with a discrete fermion number symmetry. And again, your whole current inflow picture would break down.
So, sorry, I mean, there's no current inflow, but there's still anomaly.
Yes. So what we say is that let's not think about that. This is a different way of looking at those systems. Okay, there is anomaly, of course. Okay. So the question that I'm trying to answer is, can we construct an analog of Hall current for these free fermion theories, which have odd dimensional defects and no conserved currents? The answer is yes. I will show how to construct this current. And I will discuss this in one simple application. This is just one way of unifying different kind of edge states, not the only way. As Tim is mentioning, you can think about anomaly inflow, and that again unifies the understanding of different types of edge states. So here, so this is sort of the first step of constructing this current. So first of all, what I'm showing here is, again, a 3+1 dimensional bulk, 2+1 dimensional edge. And this is described by this relativistic fermion theory. And as you know, on the boundary, I don't have a notion of right moving and left moving fermions anymore. I just have a cone, right? So all these states here, these are massless states that I'm drawing, right, on the boundary. Now, if I pick any random state from here, it's a zero eigenvalue eigenstate of the Minkowski-Dirac operator. The whole theory, if I take the Minkowski fermion operator, these are massless eigenstates of that operator. What I want to do for the purpose of constructing this generalized Hall current is I want to count only one of these states. I don't want to count these infinite number of states. So one way of achieving that is to go to Euclidean space, in which case, these states that are away from the origin, they are not a zero eigenvalue eigenstate of the Euclidean Dirac operator anymore. But this one, which is at the origin, is still a zero eigenvalue eigenstate. So what I want to do is to take that state and relate it to the index of the Euclidean Dirac operator. I shouldn't call it the Dirac operator. Let me call it the fermion operator, okay. The Euclidean fermion operator. Now, as you know, the index is the number of zero eigenvalues of D minus the number of zero eigenvalues of D dagger. I'm writing D star, but I really mean D dagger. However, it's only normalizable states.
To understand you correctly, you start with normal 3+1 dimensional free Dirac field, right?
Yes.
But then it's make a Euclidean rotation. You
Yes.
still have a Dirac field in the Euclidean,
Yeah.
four-dimensional space.
Yes.
And now you want to go to what? To a three-dimensional boundary of this Euclidean space, or you still live in four-dimensional Euclidean?
Right now, I'm still in four-dimensional Euclidean.
Okay.
Things will change in the next few slides, but I'm still in the original space-time dimension. So now if I want to connect this state to the index, you have to remember that I only can work with normalizable states here. And so that creates a problem because that 0 eigenvalue state is not localized, so it's not normalizable. So I'm in trouble, right? The index is 0. So what you have to do is introduce some diagnostic fields to localize this state in such a way that when you take this diagnostic field to 0 at the end of your calculation, the index still remains non-zero. Okay. So I will demonstrate this in an example. This may look a little bit abstract, but it will become clear in the example.
The index is 0 on what space-time topology?
Okay. Right now, I'm just looking at infinite spacetime. And so if you solve for the eigenstate for the Euclidean operator, you can see that there's one for D, there's one for D dagger, if there is one. And sometimes you see that there is no normalizable eigenstate for either operator. Okay. So now if you assume that you have turned on appropriate diagnostic fields so that you have a non-zero index, then you can relate that index to this following formula, which I will come to. But let's first define this variable I of m, which is related to my original Euclidean operator in terms of this formula. M is some mass scale, and if you take m to 0, my claim is that this reproduces the index of the Euclidean fermion operator that you're interested in. And now, what you can do further is that you can rewrite this formula in terms of this other formula, where this K is now a matrix, which has twice the size of this Euclidean fermion operator. And so it looks kind of like a trace of a gamma chi, which is like a gamma 5 matrix in the double dimension. And this looks like a fermion operator, except now this matrix K has twice the dimension of my original fermion operator. Okay. And so now I'm going to do something with this formula further. So I was not, I cannot explain how to go from here to here, but this minus sign is a consequence of the fact that you have this gamma chi. So you can see that that's where this minus sign comes from.
So, but intuitively, why is this better than the zeta function regularization? Usually, I thought when mathematicians define the index, they use the zeta function.
Right. I am not saying that it is better.
Okay.
But m squared divided by d dagger minus it's another beta function. When m goes to 0, you see, because she's picking up only low value, right? So it's very simple.
Is this the Callias version of the index theorem?
That's what it's going to. Yes.
So I think it's better because you have a continuum of modes asymptotically, and this is the right way to recognize those.
Right.
Okay. Yeah.
Okay, so now I want to compute this I of m. And the way I'm going to do this is to write a fantasy theory, which will help me compute this I of m. So this theory is that of spinors, fermions, that are double the size of my original spinors. However, when I'm integrating over space-time, that corresponds to my original space-time dimensions. So this is a double theory which amounts to introducing an extra dimension, but the fields don't depend on it. Okay. So my gamma matrices don't correspond to the number of space-time dimensions I'm in. The gamma matrices are twice the size. Okay. And you can read off these gamma matrices just by looking at this operator K. Or you could also apply, this relation would get the corresponding gamma matrices. And now what you see here in this theory is that it has its own fermion number symmetry. And it also has a chiral symmetry in this big M going to 0 limit. And these two symmetries have nothing to do with your original theory, what symmetries your original theory had. So, in this new theory, I of m is just the trace of psi bar gamma chi psi, where psi is this new double fermion field. I can define an axial current in this theory, where gamma chi is a double gamma chi. And I can get to the word identity for this current. I should have said a chi here. I mean, this current is the same current as that. And of course, if I take the limit of m going to 0, then as you can see, index is related to the divergence of this, this axial current. So I have, hang on. So I have what I wanted to get to. I have related the divergence of a current to the index. Yes, go ahead.
But physically, can I think about this double theory? So you start with a fermion in 3+1.
You could do it in any dimension. So I'm going to do it for 1+1 in the next few slides, but you could do it for 3+1.
So you start with a fermion in some space-time dimension, and you introduce this trick to double the size of the gamma matrix. But physically, can I think about it as the boundary of some fermions, massive fermions in one dimension?
No. So the way I like to think about it, I mean, you could, I'm not sure if you can think of it as a boundary, but the way I like to think about it is, it's like you have more than one flavor of fermion. Okay. Because these fields, I could just split it in, you know, 2 flavors and rewrite this theory in original space-time dimensions. We haven't done that, but you could think of it.
So I should think about gamma chi as an internal Z2 rather than a chirality.
Some kind of flavor gamma chi. You could think of it like that.
But what are you trying to do? You're trying to compute some index?
I'm just trying to relate the index of my original fermion operator to the divergence of some current. So that's what I call the generalized Hall current. So yeah.
Mu runs over how many dimensions?
Original space-time dimensions. That's why I'm saying this is like a flavor current. Okay. So here's the simplest example. Okay. So consider the continuum version of Kitaev-Majorana chain. So this is the Minkowski-Lagrangian. This is a 1+1 dimensional. Psi is the Majorana field. And let me go to Euclidean space. This is the corresponding Lagrangian. And as you know, if I have a step function in this Majorana mass, it hosts a Majorana 0 mode. And that corresponds to the end of the chain, okay, the wire. Physically, that's what the meaning of this mass defect would be. So clearly, in this example, I don't have conserved currents. I don't have any chirality on the end because I have 0, working, the massless mode is in 0+1 dimension. So what I'm going to do now is to concentrate on this operator. So note that the fermion operator for this Majorana theory, I can split it up as some C charge conjugation matrix sigma 2 times the Dirac operator. So I'm just going to concentrate on the Dirac operator because the 0 modes of this entire C times the Dirac operator is also the 0 eigenstate solution of this combined operator is also a 0 eigenstate solution of this operator. So I will count the eigenstates of this part of the fermion operator. So in this case, what I'm going to just, I'm going to rename my variable. So M, I'm just going to call phi1. You'll see why. And now what I'm trying to do is to write down explicit edge state solutions. So this is D, that's D dagger. And phi1, I'm introducing a defect in it. M0 is greater than 0. And you can, if you try to solve for 0 eigenstate solutions, you see that there are 2 solutions for D, there are 2 solutions for D dagger.
So what's epsilon? Is that a step function?
Step function, yes.
It's a sign function, that's not step, right? You want both sides to be gapped.
Oh, sorry, sign function.
Where did I? This is
-1 on one side and 1 on the
-1 to +1. So now, as you expect, these two solutions are not normalizable in the Euclidean time direction because they are not localized in that direction. So now you can see what I'm going to do with a diagnostic field, like I had mentioned. So in the Euclidean time direction, so I'm going to introduce a perturbation basically, which I call the diagnostic field. So it's proportional to the gamma chi of the 1 + 1D theory. And I'm going to introduce a step function in that. So now, as you can expect, I'm going to be able to write down some localized solutions.
The problem with the previous solutions, if you look at condensed matter literature, if you go back one slide, please.
Yes.
You look at any paper in condensed matter, these are the solutions. What is the
There's
issue?
no problem here. It's just that the index of this fermion operator would be 0 because D and D star both have solutions, 0 eigenvalue solutions. D and D dagger, right? Both have 0 eigenvalue solutions. So in my construction, they won't be useful.
But there is the mod 2 index that appeared in condensed matter that exactly addresses this. It's
Right.
called the mod 2 index.
Yes. We don't use it, but yeah, probably there is a way to connect it.
Well, there is.
There is. It's called the mod 2
Yes.
index.
I don't know if I can construct a generalized Hall current from that. It's possible. Okay, so this is one construction that I'm doing, right? It might be possible to do it using the mod 2 index as well, but we haven't done that. Okay.
Well, but the underlying symmetry is discrete, or is the spin structure, so we don't expect there to be a current.
Right. Yeah. So I don't know the answer in that case.
But then in the next slide, what are chi's? Did
Yes,
you
yes.
introduce another Majorana fermion?
This kind?
No, the chi plus and chi minus.
Oh, sorry. Let me see. So these are the solutions of D dagger. I'm just giving
So,
them.
so now the system is a Dirac fermion?
Yeah, that there is an access.
But then it's a different system, right? You start with a single
Yes,
Majorana
yes,
fermion,
yes.
and now you change the system to
Yes.
Dirac fermion.
Yes, that's right.
Okay.
Yes.
Well, but in Dirac fermion, but then are you going to say something about the original Majorana?
Yes, so the claim is that if this entire generalized Hall current construction is going to be true only if in your original theory you had the edge states. That's the claim. If you didn't have that in your original Majorana theory, then these states would the generalized Hall current would just go to 0.
If the idea, I'm just trying to understand the qualitative idea, you embed it in a Dirac fermion, and then the Z2 that acts on the Majorana becomes part of the U1, and the U1 has a current. Is that
So in this case, the Majorana fermion Z2 symmetry is not becoming a U1. So what is happening here is
I
that
know that it doesn't, but in your doubling, it will become part
Yes.
of the U1.
yes, yes,
Then there is an index theorem.
yes, yes.
Is that the point?
Yes, that's the point. So in that case, I can relate the index of the fermion operator that I'm constructing with this, adding this diagnostic fields and so on. I can connect it to a current, basically.
But this doesn't always work. There are many discrete anomalies that cannot be understood by embedding in continuous symmetries.
That's right.
Many examples of this appear.
Yes, but I don't know if, so I have not applied this to those theories. So as you can see, I'm constructing an imaginary theory, right? So I don't know if it would work or not. We hope that it would work because this is like a flavor current, right? What I'm trying to write.
Yeah, one concrete example is to consider Z2 internal symmetry
Yes.
of a 1 + 1D fermionic system.
Okay.
And half of the anomalies cannot be embedded into a U1 global.
Yeah, there is a mod 8 classification, and the odd ones cannot be embedded in continuous symmetries.
Exactly.
Okay.
You have 15 minutes including discussion, yeah?
Yeah.
15 minutes.
Okay, so if I introduce these diagnostic fields with a step function in x0, the time dimension, now you can solve again for these, the 0 eigenvalue states of D and D dagger. And what you can see is that one of the states of the operator D, which I had written out earlier, becomes normalizable. and the other 3 remain not normalizable still. Okay, so D dagger doesn't have any normalizable solution. D has 1. So I have ended up with a case where I have a non-zero index. Okay. So this was, you know, when I had phi 20, I had this kind of a profile for my 0 eigenvalue states. Now I have gotten one state that's completely localized, and so normalizable. So what you see, if you actually did the calculation, is that if you flip the signs of the profiles of phi 1 and phi 2, that is the Dirac mass and this diagnostic field, again, you would get a 0 mode for D and none for D dagger. So again, you would get an index of 1. But if you flip the sign of either phi 1 or phi 2, then the 0 mode of D disappears. You get a 0 mode for D dagger. So you get an index of -1. So there's a simple way of understanding what's going on here. So let's say I take my original phi 1 field, and then I take the diagnostic field and I rewrite it in terms of some radial component and a phase. Okay, this complex number, I can rewrite it like this. And what you can see is that if I have a cross domain wall configuration, which is what I showed you earlier, then this alpha actually has a non-zero winding along that around that cross domain wall configuration. So what you see is that alpha winds by plus or minus 2 pi as one travels around the contour around the center. Okay. So when mu0 and m0 are both greater than 0, alpha is plus 2 pi. When they are both less than 0, alpha is again plus 2 pi. If one of them is greater than 0 and the other less than 0, you get minus 2 pi. So practically what you see is that the index equals to the winding of this angular variable. Okay. So now the question is, fine, we have a fermion operator which has a non-zero winding and as a non-zero index. What does, does the generalized Hall current, whose construction I showed you earlier, reproduce the same result? Okay. So the generalized Hall current for this example, you can compute by start with this K, doubled K matrix, where D is this operator, D dagger, just take the dagger of this and you can get the K matrix. This is my double theory. And I'm now going to compute this generalized Hall current by perturbing in the field alpha. Okay, so I'm going to assume that it varies slowly. So I'm going to take my original K matrix and split it up in 2 parts. Okay, so K0 is going to be whatever remains once you have expanded in alpha. So delta K is the perturbation. All right, so I have just taken my K matrix, which depended on phi 1 and phi 2, rewritten like this, and then expanded in alpha. And so now in this theory, I can compute J mu chi, and I have a single insertion of alpha here. And so to do this manipulation, K0 inverse are the fermion propagators or on my double theory, and it simplifies to a form that looks like this. And now if you compute the divergence of this and integrate over all space, it just computes the winding in alpha. So as you can see, the generalized Hall current is proportional to the winding. So you have now the Hall current description that I wanted to arrive at. So this I won't take too much time here. A question that you can ask is, why is this Feynman diagram giving you a quantized result? And the answer to this is similar to the TKNN result, if you're familiar with this. So the divergence of this Hall current through this Feynman diagram computes the winding of a map from a sphere to sphere. So that's why you get an integer out of this Feynman diagram calculation. So here's the conclusion. We have constructed a Hall current analog for Majorana zero modes living in 0+1 dimensions. This construction works well for all free fermion theories that we tried. If you use appropriate diagnostic fields, we use one loop Feynman diagrams to construct this generalized Hall current. In all cases, it computes a winding of a map from sphere to sphere. The divergence of this Hall current correctly reproduces the index of the fermion operator. Some of the other examples we worked out are 2+1 dimensional surface states of 3-dimensional topological insulators, then 2 flavors of Majorana fermions without time reversal symmetry, where you know that the fermions are gapped. So even that you can capture. So the generalized Hall current disappears as soon as you turn on this time reversal breaking mass. And then 2+1 dimensional Dirac fermion theory with pairing, which hosts chiral edge states on the boundaries, 1+1 dimensional boundaries. These are chiral, rather Majorana wild fermions. So you can construct a Hall current even for that. Follow-up work is how does one incorporate interactions in this generalized Hall current picture? In some cases, as you know, interactions can change the topological classification of phases, and boundary states can be gapped out by turning on interactions. Can this be captured using generalized Hall current? We are trying to work this out. The answer is most likely yes. How do you realize this on the lattice? Can that help with realization of chiral gauge theories on the lattice? And finally, I have taken this from Wikipedia. Apparently, all topological superconductors and insulators are characterized by 4 invariants: Chern number, Wess-Zumino winding number, Chern-Simons invariant, and Fouquet invariant. What is the connection between those and the generalized Hall current that we computed? So these are some of the questions we are thinking about, and thanks for paying attention. Yeah.
I'm a little bit confused. I mean, in the example you gave, I mean, there is no current, and then you double the degrees of freedom, and now there's a current, but it doesn't relate to the original system. And moreover, they are protected mod 2, right? These, so here, when you're doubling the number of, if you're not imposing an additional symmetry, when you're doubling degrees of freedom, then you should be able to lift these moves.
Yes. So the question is, how do you see this in the generalized Hall current construction? So I haven't discussed this here in this talk, can you see the lifting mod 2? Okay, so can the generalized Hall current, if you computed its divergence, would it go to 0, right?
But naively, no. If you double again, you know, if you consider 2 Majorana from the get-go,
yes,
without the symmetry, then you can get much, right? Without some U1 symmetry.
Yes. So
not to combine them to a Dirac fermion, because then the symmetry is.
Yeah. So there are ways to do it. So in one example, I did it, right? So this one I didn't discuss yet explicitly, which is this one where you have, you know, if you have 2 Majorana edge states on the boundary, you can turn on a time reversal breaking term, which gaps out the 2 Majoranas, and you can show that in that case, the generalized Hall current actually does go to 0. But the particular example that you're talking about, I have to see how that works. I'm not sure, but it may work out. Yeah.
What about in the case of 2+1 dimension? That is protected by time reversal symmetry and the U1 symmetry, and that's a mod 2 effect again.
Yes.
So you know it's very difficult to imagine that that this is protected by a inflow current.
So one thing that you have to remember for this generalized Hall current is I'm turning on a background diagnostic field, right? And I'm taking it to 0 at the end of my calculation. So every time you turn on a perturbation, that would gap out your edge states. as soon as that becomes, the strength of that becomes larger than the diagnostic field that I'm turning on, my generalized Hall current goes to 0, or rather its divergence goes to 0. Okay, so that is one way of seeing the behavior of this gapping in this picture. Okay, so the one example where I have this worked out, it just happens to be the case that the time reversal breaking, which gaps out my original fermions, as soon as its strength is larger than this phi2 field that I have turned on, my generalized Hall current goes to 0. So it turns, the examples that we worked out, we see that if you have a mechanism by which you can gap out the edge states of your original theory, if you can turn on such a perturbation and it gaps out the states of your original theory, it immediately implies something for my imaginary theory. So it has a one-to-one correspondence because immediately the index of that operator also goes to 0. The index of this modified theory that I'm looking at with this diagnostic field, because the diagnostic fields I'm always, I'm taking it to 0 at the end of my calculation. So as soon as you have a perturbation that perturbs the original theory, it perturbs my generalized Hall current and this double theory. So that's how I would translate one with the behavior of one without two other. Yeah.
Yeah. I think I share the same confusion about why do we want to force every topological phase into a generalized Hall current? And there are topological phase associated with non-abelian discrete symmetry, right?
Yes.
S3, dihedral group. Then there's absolutely no way for us to embed that into something.
I don't know the answer. So this is the thing. Here is I'm saying that this is a flavor current. It's not there in your original theory. Okay.
Yeah.
Why do I want to do it? Because I like it, right? This is a picture that I like. Okay. Because it helps me understand in a physical way what is going on. Okay. This is not
apply to all topological phases.
Sorry.
But it will not apply to.
So for now, we have applied it to many more than you would have expected. And I cannot say for sure if it would apply to everything, but we believe that it's possible because what I'm showing you here is a flavor current. It doesn't exist in your original theory, okay?
But a discrete non-abelian finite group cannot be embedded into one. So
maybe one comment is, if you go back to kind of the original classification of topological insulators and superconductors, focused on a set of symmetries that are kind of like natural in condensed matter physics, which was, basically time reversal, charge conjugation, fermion parity. And so it may be that if you're interested in those, in that classification, so
those might be able.
Yeah, like I agree. If you're able to think about any internal symmetry you want, but the classification is much more complicated. But those ones may fall under this umbrella.
Okay, last question. Okay, if not,
yeah. But it is. Nevertheless, that is one that which is not a
I think that there is kind of another way to formulate. If you're talking about, say, this field will have, but it doesn't change the energy. It does not. Right. So you have to non-vector state, you have to different.
Thank you very much.